Hello, everyone, and welcome to the April 2021 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll, and we're once again in the format where we're getting way too many questions for the AMA. For those of you who don't know, questions are asked by Patreon supporters. So you can go to patreon.com/Sean M. Carroll. And if you want to support Mindscape, that's always a good thing. And some fraction of the people who support on Patreon like to ask questions. So we have the monthly AMA. There are too many questions for me to really feasibly answer all of them, or even almost all of them. So I'm trying these days to go through, pick out some, group some together, and so forth. And look, it breaks my heart, honestly. Like, I would like to answer all these questions, but I have to pick and choose. And what I want to emphasize is, it's not you, it's me if I'm not answering your question. It's not that the questions aren't good. Really, the questions are all good. I could try to answer any of them. But what I'm trying to do when I'm picking questions to answer is pick the questions that I have something interesting to say about. So that it's not only useful for the asker, but also for the people who are listening. Hopefully people listen to the content here and get something out of it. So either it's a perfectly good question that I'm just not inspired to say anything interesting about, or it's a perfectly good question that someone else could answer, or you could Google or Wikipedia or whatever. Those are not the questions I'm going to answer. And in addition, of course, as I say in the call for questions, I'm not going to do any work to answer these questions. So if it's like, read this person's theory and tell me what you think, that's never going to happen. Sorry about that. Again, I would like to, in a world of infinite resources or multiple copies of myself that I could then talk to and get information from, I would be able to do that. In the version of many worlds in which we actually live, I don't get to talk to the other selves that are doing all this work out there, so they're kind of useless. Anyway, having said all that, lots of good questions today, so let's go. I wanted to start with this news report that we recently had that the Large Hadron Collider, in particular the LHC-B experiment at CERN, has an anomaly. It has a result that does not exactly fit into the standard model of particle physics. And a couple people asked about it. Joy Kolbach, Maxime Alexandrovich, Michael Rinaldi all asked different questions about it. And I don't want to go into too much detail about it because I think that I can probably use it as a jumping off point for either for talking to someone, maybe just talking to myself as a solo episode, but for digging in deeply into related issues about the standard model and how it works and what we expect from it, things like that. I'm not sure that I'm going to do that, but it's a prospect. So rather than spending half an hour, 20 minutes explaining it here, let me just note that. I'll give you the 30-second version here. What they found is that there's a certain decay of a certain kind of quark, the bottom quark. Joy asked, what happened to the beauty quark? Didn't we used to call it the beauty quark? Early in the days when you either hypothesize or discover a new particle, people will try to name it. There's some kind of collective intelligence action that goes on, and you decide what to pick. So the third generation of quarks, some people wanted to call them truth and beauty. Other people want to call them top and bottom, and the less evocative names won. I wasn't there for that discussion, so I'm not exactly sure why they chose that, but there you go. Anyway, the prediction of the standard model is that to a very good approximation, the bottom quark should couple the same to things like electrons and muons. That's basically because the coupling is through things like W and Z bosons, and those couple exactly the same. But you could imagine that if there was a new particle that coupled to the bottom quark and to electrons and muons, then the decay of the bottom quark into electrons or muons would be a little bit different, right? A ratio that was not quite one of the number of electrons produced to the number of muons produced. And that is apparently what they are seeing. So the question is it real or will it go away? It is a 3 sigma event, if you're familiar with that statistical nomenclature, which means, it's worth paying attention to, but we don't know if it's going to survive or not. So I always preach patience in these cases. It would be easy to explain if it were real, easy in terms of we would need to introduce new physics to explain it, but it's not hard to invent versions of new physics that would do the job. You just need a particle that a virtual particle inside the Feynman diagram, as it were, that would couple to bottom quarks and differently to muons and electrons. The Higgs boson does that. The Higgs boson is an example. In this particular decay, the Higgs boson just plays a very, very tiny role. But if there's a particle that is more important to affecting that, then that'll be really, really interesting. In fact, the bad thing is there are too many ways to explain it. So if it's just that one little fact, even if it becomes true, you don't then get to say, oh, it's supersymmetry, or oh, it's grand unification, or oh, it's whatever, because there's more than one way of doing it. So I would say, hold on, try to collect more data, see where things are going. Douglas Albrecht asks, have you or others speculated what might be emergent properties at much larger distances and timescales than we are accustomed to considering? Is there a reason not to think that there might be radically different emergent phenomena if we were somehow able to appreciate our universe from this kind of perspective? So if I understand correctly, what you're saying is, if I understand it, which I'm not sure, but what we know is that, we're made of atoms and things like that, and these atoms come together to make molecules and cells and organs and bodies, and then the bodies come together to make groups and societies and civilizations. And so as you go to bigger and bigger levels, you get different kinds of emergent descriptions of what's going on. And the question is, could we imagine going to bigger and bigger levels, right? Much bigger than planets or people or maybe galaxies? Well, I actually think the answer is no here. I mean, it's a very good question to ask. It's a perfectly reasonable thing to wonder. I suspect the answer is no for the following reasons. Number one, we know a little bit about things on the scale of galaxies, right? And, galaxies in the universe are pretty far apart from each other. In a cluster of galaxies, they can be very nearby and they bump into each other all the time. The Milky Way is going to bump into Andromeda, but individual galaxies out in the field are far away from each other and don't bump into each other, and clusters generally don't bump into each other. So galaxies just don't interact that much, right? I mean, part of getting an emergent phenomenon is that not only you're on a big length scale, but the little individual pieces of which you're made are constantly interacting, right? Are constantly bumping into each other. So rather than describing them as just individual pieces occasionally interacting, there's some average behavior that can emerge. When the individual pieces only occasionally interact, that doesn't become a useful way of talking. And the other thing is, on very large scales, much larger than galaxies or the universe is just not that old, right? We have the Big Bang 14 billion years ago, and the visible universe is some tens of billions of light years across, which means, which by the way, those two numbers are not the same. The size of the visible universe is not exactly the age of the universe in light years, because the universe is expanding and there's a complicated interaction there going on. But roughly speaking, order of magnitude, the size of the visible universe in light years is the same as the age of the universe measured in years, which means that on scales larger than the observable universe, there's been literally no interaction. There's not been enough time for things to interact very often, and there won't be. The universe is accelerating. So the things that have not yet interacted, that are on cosmological distances from each other, will never interact, roughly speaking, with each other. So there's no chance, there's no opportunity for these things to come together and be described in an interesting way as an emergent phenomenon. That's my take on it, and I hope that I'm answering the question you're actually asking. Adrian says, you strike me as someone with a special talent for expressing even controversial ideas in a very diplomatic and respectful manner. It's probably easier when debating intellectuals, but do you have any tips for someone who has trouble staying calm and not getting angry when debating, let's say, a close family member with some rather non-standard ideas about epidemiology and virology? Well, thank you for the compliment of having the talent for expressing even controversial ideas. And I don't have any simple, basic rules for these kind of situation. I think the first thing to ask yourself is, what kind of situation are you actually in? Look, sometimes people don't want to be reasoned with, right? Some people are just not in it for an intellectual debate. Some people are not open-minded about certain beliefs that they have, either those particular beliefs or those particular people more generally. And in that case, save your breath. Don't waste your effort, right? One of the things that makes me able to talk to people with whom I disagree is that the people who I choose to talk to are people who can be talked to, right? People who can be reasoned with, people who are saying, well, I think this, but let's talk about it. Let's actually reason. I'm willing to listen to what you have to say. And, I'm too old to just sort of debate people who I don't agree with. As I said before, for the podcast, I specifically will occasionally bring people on who I disagree with, but only if I think that their ideas are somehow worth contemplating. I think it's possible to disagree with someone and yet say that their ideas are not worthless, right? We have to admit that we could sometimes be wrong. If you're going to ask your interlocutor or your partner to admit that they could be wrong, you got to admit that maybe you could be wrong also. So the people I bring onto Mindscape are ones who I think we can all learn from, or at least provoke interesting ideas in our head, whether I agree with them or not. I will and have, of course, done formal debates with people I deeply disagree with, but I'm not trying to convince that person that they're wrong. They're, up there on stage making a performative act in whatever they believe. I'm trying to reach the audience, right? When I debated William Lane Craig, there were a lot of people in the audience who were, young people who might have been religious who had just never heard the perspective of an atheist who was a reasonable person with some answers to the questions that might have been bugging them. So the purpose of a debate like that is not for me to win the debate or to convince the other person. It's to put some ideas into the head of audience members who might not have otherwise heard them. Now, family members are a different issue, right? Because on the one hand, you kind of have to deal with them and you want to. They're in your family, you care about them. On the other hand, they might not be rational or reasonable. And I don't have advice about how to not get angry. I think it's good not to get angry. I mean, that kind of advice should come from, I don't know, either a psychologist or a Zen master or somebody like that. But I agree that you should aspire to not getting angry. It never helps to get angry with people when you're just debating about something. There are people who like to debate not because they have irrational beliefs that they were going to stick to, but because they have no beliefs at all. They just like to win debates. Those people to me are just as annoying as the ones who have irrational beliefs that they're going to stick to. Like I'm not interested in that. My participating in debates is always about raising the overall understanding of the world on the part of either the people participating or the people listening. It's never about showing off some intellectual chops or anything like that. So if you find those people who are just like to debate, then, again, I would just choose to do other things. As far as your family members, you have to remember that you do care about them. And sometimes, even though you care about them, they're going to be wrong and you're going to live with that, right? Forget about people with opinions about vaccines or something like that. This very often happens when you have very elderly relatives, whether it's parents or grandparents or whatever, and, they want to live their lives in a certain way and you don't agree. Like you think that they're taking risks or something like that. They're not using their remaining days in the best way possible. And my attitude there is that if someone is not endangering others, like I don't want people who can't drive anymore to be driving, right? That would be bad. But if people choose to, live a lifestyle when they're older that is maybe a little bit riskier to their health, but makes them much, much happier, let them do it. That's my philosophy. I think the motto is autonomy is more important than rationality when you get to that point in your life. When you're to the point in your life where you don't have many years left, let people live their lives. Obviously, if they're suffering from dementia or something like that, or like I said, if they're a danger to others, that would not count. But if people are relatively in control of their faculties, I like to let people make choices that are their choices, even if it's not the choices I would wish they could make. I know that's not the question you asked, but I sort of got rambling there. Sorry about that. Brian Davis says, if dark matter did not exist nor any of its observed effects, do you think that the resulting conditions would have allowed for life to emerge? So this is sneakily a really good question. I don't know, Brian, if you know the story here, but for life as we know it right now, here on Earth, dark matter plays zero role, okay? If all the dark matter in the universe disappeared right now, you and I would not even notice. It would certainly not affect our lives. But it is possible that dark matter played a role in creating the first generation of stars. I mean, we know that dark matter had a role creating the first generation of galaxies, right? But dark matter doesn't like to clump together, as I've said before on the podcast. So dark matter doesn't clump together into star-like things. But yet people have suggested that maybe the combination of dark matter dynamics and ordinary matter dynamics in the early universe helped create really big stars in the very first generation, and then those would explode and create heavier elements and lead to other star formation down the line, etc. So I don't know what the answer is to your question, but it is conceivable to me that without dark matter, life, the kinds of stars and planets that support life would at least be much more rare in the universe than they are. I don't know if it would be impossible. Usually it's not impossible. We have a big universe out there, right? So maybe without dark matter, stars would be much less common, but they would still be there occasionally in the universe. Okay, I'm going to group together 4 different questions. Let me just ask them all explicitly here. Hopefully the theme will come through. Chris Rogers says, is gravity a force? Eugene Novikov says, we lay people are taught using trampoline analogies that gravity is the manifestation of the curvature of space-time itself. That seems conceptually very different from the idea that gravity is a force mediated by an elementary particle called a graviton. How should we think about the relationship between these ideas? Sean Atkinson says, I understand we are confident that gravity must be communicated via an additional quantum particle referred to as the gravitino, and it's just a matter of discovery. But I've also heard on multiple occasions that gravity is not so much a regular force, but rather how space-time is curved. These explanations have always felt like some kind of contradiction. Am I missing something? And Anonymous says, I have a question about what it means for space to be curved. If I put a cantaloupe on an empty cereal box, that's a very specific analogy, by the way, but if you put a cantaloupe on an empty cereal box, the surface of the box will bend inward and curve. But I could still think of the box as curved with respect to rigid 3-dimensional coordinates. Can space be thought of as a curved medium that's completely filling true empty space, like a bunched up scarf inside a shoebox? Or is there just the scarf? Okay, so I hope you get the theme of what is gravity and what is curvature of space-time. Is it really a force? Is it really a particle? Of these 4 questions. It's interesting, maybe someone could do some deep learning analysis of the AMA questions and why certain topics pop up multiple times. Something in the air? I don't know, someone out there talking about curved space-time and is gravity a force? So, when I was young, when I was your age, I was pretty doctrinaire about saying gravity is not a force once you understand general relativity. And the reason for saying that is that Einstein's great insight in general relativity is that so he already had the insight, he didn't have the insight, but due to special relativity, Hermann Minkowski, Einstein's former teacher, had the insight that we should dissolve space and time separately and make them into one 4-dimensional space-time. Einstein was reluctant to accept that, but eventually accepted it and said, you know what? Gravity is not a force propagating on top of space-time. It is a feature of space-time itself, okay? So there's a way of thinking that says we should separate out forces that live within space-time, like electromagnetism and the nuclear forces, from features of space-time itself. And this helps understand the principle of equivalence. If you're in a small region of space, you can't even tell whether you're in a gravitational field or not. Space-time, I should say. Whereas you can tell if there's an electric field or if there's a magnetic field or something like that. So that's the justification for saying that you shouldn't think of gravity as a force. But, I'm in my old age, in my dotage, I'm much more open-minded about these things. Sure, gravity is a force in some sense. When I drop this pen that is right in front of me, if I drop it, there, you heard it drop, it fell on the desk. I can describe that as the force of gravity pulling on the pen. That's not a bad or illegal move to make. So the point is that the idea of a force, or any idea like force, or energy, or acceleration, or any of these things, these are not pre-theoretic ideas, okay? All of these ideas are words that we invent in the context of some understanding of the world. And maybe within some sort of way of talking, they're useful words. Some other way of talking, they're not. The best way we have of describing gravity in the macroscopic classical world is as the curvature of space-time. If you want to therefore say it's not a force, it's not a particle, it's the curvature of space-time, fine. But there could very well be other circumstances, either more limited or more specialized or more general, where there's another way of talking about gravity. So you can also, here in the room where the Newtonian approximation is really, really good, talking about gravity as a force is perfectly fine. Talking about it as a particle being exchanged, as the exchange of a graviton, is also perfectly fine. It's exactly analogous to how we talk about electromagnetism and electromagnetic fields, or we talk about the exchange of individual gravitons. So one of the questions called it the gravitino. That's not right. That is definitely a mistake. So it's called the graviton, the particle of gravity. Gravitino would be the supersymmetric partner of the graviton, if such a thing exists. We've never discovered either one. So gravitinos are truly hypothetical. Gravitons almost certainly exist. I say almost certainly because quantum mechanics is correct and gravity is correct. And if you believe both of those things, there's going to be a particle called the graviton. It's just too weakly interacting with us for us to ever realistically discover individual gravitons, unless something crazy happens like gravity becomes much stronger at higher energies, which is possible, but not very likely these days. So it's not that it's a contradiction. It's just there's two different languages for describing the same thing. Now, one more piece of physics I need to say, and I forget. I might have erased by mistake the question about this, but or it might be later, so I might be answering it earlier than necessary here. But here is a question you could reasonably have. When you draw like a Feynman diagram, and you imagine two electrons, okay? And the electrons approach each other and they exchange a photon and they scatter, okay? That makes sense. Like it makes sense from an intuitive point of view. You know, if you have two people on a boat, on two different boats, and they're sort of moving through the lake and it's not very windy or anything, and one of them throws a medicine ball to the other, the one who throws, you know, there's some momentum imparted to that medicine ball and it pushes them in the other direction. And likewise, the one who catches it is pushed in the other direction. So by the exchange of the medicine ball, the two little boats, the two little canoes are pushed apart. That makes sense. Much like two little electrons are pushed apart by the electromagnetic force. But if you have an electron and a positron, or if you have two objects exchanging gravitons, they're not pushed apart. They're pulled together. How in the world do you pull something together by throwing something back and forth, right? It seems like the only thing you could do is push yourself apart. The secret is that virtual particles, I discussed this in the Biggest Ideas in the Universe videos, virtual particles don't necessarily have a positive value of the momentum. You can throw a virtual particle from one particle to another one with a negative momentum. When you throw a particle with a negative momentum in some direction, you start moving in that direction to conserve momentum, right? And this is all, the math all works out. It's a little bit counterintuitive, but trust me on that. I just want to let you know there's a little bit of counterintuitive goings on that help explain how you can get both attractive and repulsive forces from exchange of particles in Feynman diagrams. And finally, to the space versus the scarf question. So what I take it here is being asked is when we visualize curved spaces or surfaces, we inevitably do it as a two-dimensional surface being bent, you know, like the rubber sheet with the bowling ball on it, embedded in a three-dimensional space that we live, right? And that is entirely a feature of our visualization capacities. That is not a feature of nature. So we do not think that because our three-dimensional space or our four-dimensional space-time is curved, that it therefore must be embedded in a higher dimensional flat space-time. This was really the insight that came from the 1800s when Gauss and Riemann and others discovered how to do intrinsic geometry rather than extrinsic geometry. The extrinsic geometry is talking about how you're embedded in a bigger space. Intrinsic geometry is just what's going on to you internally in the space that you're in. And you don't need to be embedded in any bigger space. You can ask questions like, if I start two photons off and they're initially parallel, do they converge on each other? Do they get deflected away from each other? Do they twist in some direction? These are all askable questions, and they're all answerable questions from the perspective of someone inside the space. You don't need to be embedded in a bigger space outside. And that's kind of what we do when we do general relativity. That's essentially the kind of thought experiment that we're doing in some more technically relevant way to some real physical situation. So we don't need anything outside. When the universe is expanding, when it's curved, etc., that does not imply there's any other universe that it is part of or that we're embedded in. Oh yeah, it's right here. It's the very next question. Should have been grouped into there. It's from Thomas Prunty. He says, in last month's AMA, you talked about how a classical field arises from a collection of bosons. How then would you describe the corresponding force in terms of particles? For example, how does the classical electrostatic force arise from exchange of photons? What makes it attractive or repulsive? So there you go. That's what it is. The details are in things like the charge of the particles, right? And that affects the value of the Feynman diagram that you calculate. And beyond that, at the level of this AMA with no pictures or no equations, I'm going to have to say, trust me on that. But it all does fit together. It's all, you should think of tiny little fluctuations in fields as corresponding to particles and big coherent bending or expectation values of fields as corresponding to classical fields that you would notice in your everyday life. Okay, Gerald Swan says, regarding the Fermi paradox, do you think it's plausible that other technological civilizations exist, but interstellar travel is simply intractable engineering? No, I don't really think that that's a very viable solution. I don't think that interstellar travel is intractable engineering. I mean, look, even we puny humans have sent spacecraft outside the solar system, right? The Voyagers, the Pioneers, etc. Now, they're moving very, very slowly, but we really are very backward right now compared to where we could imagine being in terms of rocket propulsion, etc. The other thing you have to keep in mind is that, everyone worries about the speed of light. It takes years or tens of years or hundreds of years to travel from our solar system to other solar systems at reasonable fractions of the speed of light. That sounds like a long time. What if it takes 10,000 years to get to the star you want to get to? Well, that's fine. You won't survive, right? But number one, maybe you will survive because maybe we'll solve longevity of human beings. Maybe we'll be able to solve aging. That's a possibility. Number two, there could be cryogenic suspended animation. Number three, we could just send robots. Most importantly, 10,000 years is nothing compared to the lifespan of a planet or a star or the galaxy, right? So I don't see any reason why you should think that interstellar travel is so hard that no one has left their solar system. That maybe it's true. I mean, anything's possible. I don't know for sure, but that would not be the way that I would bet. Justin Bailey says, would you summarize how you avoid the Boltzmann brain paradox in your view of the universe? I don't have a view of the universe once and for all. I, as a theoretical physicist, investigate different scenarios, right? We propose different hypotheses and we try to figure out which ones are the best fit to the data. So I'm not sure if you mean specifically, I did with Jennifer Chen propose in 2004 a view of the multiverse, where baby universes were created from quantum fluctuations in empty space, and those baby universes grew up into big inflationary universes. So in that particular situation, the reason why you avoid the Boltzmann brain problem is because you create Boltzmann brains, very plausibly. You also create universes, and those universes grow up and create lots of ordinary observers. And the point is you can show that you create more universes than brains. A universe, that sounds like a lot to create, sounds like harder to create, but in fact, this is the miracle of inflationary cosmology and general relativity for that matter. Creating a universe is not that hard. Universes can start really, really tiny, okay, near the Planck scale. They can inflate upward to whatever size you want, and the total amount of energy it costs to create a universe is zero. That's a tricky thing because there's both negative energy and positive energy in general relativity, much like, but not exactly like the negative and positive momenta inside Feynman diagrams that we just talked about. So the point is that if you just calculate the chance that you will get a random quantum fluctuation into a brain or a living being, that is lower than the chance you will get a random quantum fluctuation into a little bubble ready to make a whole universe. And every bubble corresponds maybe to billions or trillions or quadrillions of ordinary observers. So the hope is that to the extent that it's possible to compare them, you make more ordinary observers than Boltzmann brains. Now, I don't necessarily think that scenario is right. I think it's possibly right. I think there's a credence that you should have that something like that is on the right track, but we don't know for sure, certainly. So I'm not sure if that's the right way that the universe avoids the Boltzmann brain problem. I think there's, roughly speaking, two possibilities. The Boltzmann brain problem arises when you have a universe that lasts forever and randomly fluctuates. Okay, so there's going to be random fluctuations. Then you're more likely overall to get if you have a finite number of things that can happen in the universe, then small fluctuations away from equilibrium will always be more likely than large fluctuations. That's when you get the Boltzmann brain problem. When you have a finite number of things that can happen and an infinite amount of time for them to happen in. So that's why I said there's, roughly speaking, two ways out. One way is have an infinite number of things that can happen, not just a finite way. That's what we take advantage of in our scenario. But the other way is to not let the universe last forever. Have a universe that really, not just within our observable universe, but overall lasts a finite time. Then it's very, very easy to have more ordinary observers than Boltzmann brains. Which one is actually true? I don't know. We have to think about that. We have a long way to go to really have confidence one way or the other. Per Magnuson says, what are your thoughts on the possibility and time frame of a future technological singularity? It seems to me like we are making very fast technological progress in some regards, but in others we seem to have picked most of the low-hanging fruit and progress is not obviously exponential. Yeah, I have zero credence, not quite zero, but almost zero in a future technological singularity. Of course, it depends on what you mean, but I take it at face value that a technological singularity is really equivalent to an essentially infinite rate of progress in technology. And that is what people have tried to argue for. But there's no way to quantify rate of progress in technology. I mean, there's no one way that captures everything. You can invent ways, but a lot of it has just been hand-waving, honestly. And I think that besides just being hand-waving and ungrounded optimism, the other problem is that people take, exponential growth curves and just extrapolate them. By the way, you need worse than exponential. You need, not worse, better than exponential to get a singularity, right? An exponential is not a singularity. An exponential just keeps growing forever. A singularity is like 1 over x. As you approach x from the left, it goes to infinity in a finite interval. That's what you would need for a singularity. And even if you had super exponential growth, you could only have that for a little time. There's no guarantee whatsoever that you have it forever. There are plenty of examples in nature of, yeast growth curves, which kind of look like bell curves, where you exponentially grow, but then you peak and you go back down to zero. That's a very plausible future scenario. You also have sigmoid curves, where you grow for a while exponentially, but then you flatten off and are just flat for a long time in a new equilibrium. If you go back to one of my favorite Mindscape episodes with Joe Walston about the environment and urbanization, and we talked about the fact that we could be in the midst of a transition between two equilibria, where one equilibrium has no urbanization and no technology, right? And so, people were just animals just like everything else, and the earth went along perfectly fine. But then we discovered technology, and we began to exponentially change our lives. But it's possible that we're just approaching a new equilibrium where most people live in cities. Most of the earth is not urbanized at all, and there's no people living there. There's the rest of the ecosystem living there. And we live happily in our cities, and we interact with the outside world, but we don't ruin it and despoil it as we so often do these days. Like you imply in your question, there are some areas in which we picked most of low-hanging fruit. I think that's absolutely true. Atoms are the smallest thing we can make things out of. I mean, electrons, okay. Electrons are nuclei, etc. But you can't get smaller than that technologically. So once you reach the point where you are manipulating individual atoms and individual particles, all future progress is made from putting those basic pieces together in more and more interesting ways, not in getting smaller in the fundamental pieces from which you're building your technology. There's plenty of room for improvement, but still there are some particular, particular avenues of improvement that are no longer open to us and that won't be open to us. That doesn't mean that improvement stops, but it just means that you need to do it in other directions, right? And it's completely plausible to me that, we improve technology for a while and then we stop improving it. We're not almost there. It's not like we're going to happen in the next 10 years. But if you're thinking about the next 10,000 years, that's completely plausible to me. Sam says, are you pleased with what the Sixers did or didn't do at the trade deadline, and have you spoken to Daryl about it? By which, of course, he means Daryl Morey, who's a recent Mindscape guest. I'm pretty pleased with what they did, actually. For those of you who have not been keeping track, the Sixers were rumored to be part of a blockbuster trade deal with the Toronto Raptors to get Kyle Lowry, but it turns out that they would have had to trade a lot of their existing players and future draft picks, and they didn't do it. They thought it wasn't worth it, and I think that's the correct choice. I did not speak to Daryl about it. The Sixers did pick up George Hill, who's a good, second choice, I think, a good shooting point guard who can play defense. And the reason why I'm asking these questions is not because I have anything especially insightful to say about the Sixers or that most of you care about that, but, I do think there's something to be said about how much you bug people. And, I take, some people who I have on the podcast are people who I know personally. We hang out, right? We see at conferences or we see at other, social situations. And other people I have on the podcast, when I have, Wynton Marsalis or Cornell West or Daryl Morey or Seth MacFarlane, I'm not buddies with these people. We got along really, really well for the podcast episode, but I'm not going to, constantly pester them with my opinions about their job. I think that is, part of the bargain is that you respect other people's time and space. If the people are especially really, really busy, working at a high level in some particular profession, if we happen to meet up and have a drink together and, chat, then I might do that. But I'm not going to be DMing Daryl Morey with my opinions about the Sixers trade deadline. He deserves better than that. What do I know? Okay. He has not DM'd me about his favorite theories of dark matter either, just so you know. Dragon-Sided D says, could you briefly compare and contrast the work with you and Alan Guth on a two-headed arrow of time at the Big Bang with Neil Turok and collaborators' CPT symmetrical theory? It looks like both posit basically two equal and opposite universes resulting from the Big Bang. Are they compatible theories? So here's the bigger story here for those of you who don't know what this is referring to. As I said, in 2004, Jennifer Chen and I proposed this very specific model with baby universes. And the motivation for that model was to make realistic the idea that there is an infinite number of things that can happen in the universe and an infinite amount of time for them to happen, okay? You can do that in a trivial way. Have a universe with 3 particles in it, and space is infinitely big, and the particles sort of, come together, and they just zoom off to infinity forever. So in some trivial sense, that's a universe where things are always changing because the particles are always getting further and further away. And what happens in a universe like that is that there will always be a moment. If you just have 3 particles, again, they're not, forget about gravity, okay? Just 3 particles that are moving on straight lines. 3 particles moving on straight lines through the universe always have the property that there was a moment when they were closest. There's a single moment when they're closest, whatever else you're going to do, no matter what their specific trajectories are. And in both the past and the future of that moment, they're further apart. So you can kind of use this behavior as a metaphor, as an analogy for the behavior of entropy when you have many, many, many more particles or more quantum degrees of freedom or whatever. So the idea is that if time lasts forever and you have a universe that can always be changing, the generic behavior you expect is that there is a moment of minimum entropy, and entropy is increasing both to the past of that moment and to the future of that moment. So you're not tuning the fact that entropy is increasing. Entropy is always increasing everywhere except for literally one moment of time, okay? The question is, can you make it realistic? So what Jenny Chen and I try to do is make it realistic with baby universes and big bangs and stuff like that. This leaves more conceptual questions about how you make predictions and how you tame the infinities in such a scenario. So that's what Alan Guth and I have been working on. slowly, and my apologies to Alan in the unlikely case that he is listening to this. Both Alan and I, are very, very interested in this problem, but we're the worst people for getting things done. So we've been working on this for years and just not quite finishing the project. But it's very closely related to similar work that Julian Barber did with his collaborators on the Janus point. He wrote a whole book about it. In some classical gravitational theory, having this behavior where there's a moment of minimum entropy and it increases to the future and the past. So Alan and I are looking at the fundamental conceptual questions here. Julian and his collaborators had a specific scenario which wasn't very realistic, but at least they could solve all the equations. Jenny and I had a specific scenario where we don't have control over the equation. So we had to make guesses and cross our fingers. That's why it's much more speculative. In contrast, so Neil Turok and his collaborators, I'm sorry I forget the collaborators' names, I didn't look it up before doing this, they have a theory, and by the way, there's other people who followed up Jenny and my ideas. So Stephen Hawking with Jim Hartle and Thomas Hertog looked at bouncing or overall symmetric cosmologies within their wave function of the universe quantum cosmology program. So there's other people who've done this kind of thing. And so Neil Turok and his friends did a specific example of this where they had kind of a bounce at the middle of the history of the universe, and the universe expands and entropy grows in both directions away from it. And it's symmetric under this particle physics symmetry called CPT, charge parity time reversal symmetry. And their idea was, not only are they explaining the Big Bang cosmology, but somehow the matter-antimatter asymmetry in the universe. Our universe has more matter than antimatter. Maybe on the other side of the Big Bang, there's more antimatter than matter, something like that. So there's a huge difference between these, actually. So the similarity is that if you go to the far past and the far future, you get very similar looking cosmologies where entropy is increasing and you get an arrow of time pointing in opposite directions. But the difference is that they have a very, 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 very specific condition right there in the middle. Okay, so they're not saying this will happen for any old initial conditions. They're picking almost infinitely finely tuned initial conditions to do that. And again, other people have done the same thing long ago. Anthony Aguirre, who is a former Mindscape guest, he and Stephen Grattan wrote a paper about a completely symmetric de Sitter space-based cosmology. They didn't try to explain baryogenesis or the matter-antimatter asymmetry, but they did the general relativity and got that cosmological solution. I think that was before my paper with Jenny. But the difference is they weren't trying to explain the fine-tuning of the early entropy, and neither is Neil Turok and his friends. Like Jenny and I were specifically aimed at trying to give a dynamical explanation for the observed low entropy of our early universe. And by the way, I think it's still true, even though the scenario that Jenny and I put forward is extremely speculative and involves a whole lot of leaps of faith. It works under those assumptions, right? So it's not cheating. It's not cooking in the answer. It's not fine tuning anything. And I don't know of any other theory that does that still, 15 years later. So there's work to be done. Either we're right or someone else is right. I would like to know one way or the other. George Sarabidze says, as you know, light has zero mass, and since everything divided by zero and multiplied by zero always gives zero, gravity has to have a very little or no effect on light. However, light never chooses the shortest path route. Instead, it always chooses the shortest time route. Would it be reasonable to state that when light encounters dense galaxies, it should take less time for the light to go around the dense galaxies than through them? So there's a couple things I have to undo here. Everything divided by zero does not always give zero. So you're not allowed to divide by zero as a blatant move. You can take a limit of dividing by a really tiny number and sending that tiny number to zero. And usually you just say what you get is not a number. You get a singularity, right? But there could be special cases where things work out well and you get a finite number. But there's absolutely no rule that says when you divide by zero, you get zero, just so you know that. It's also not true that gravity has zero to no effect on light. This is one of Einstein's discoveries, right? In Newtonian gravity, you think of the mass of a particle as both its resistance to a force right, is the amount of inertia it has. F equals ma. The more massive it is, the more force you have to give to accelerate the particle. But you also, in Newtonian mechanics, think of the mass as the source of gravity. The more mass, the more gravitational field it has, and the more it is affected by a gravitational field. But that's not what Einstein says, okay? Einstein says you have the principle of equivalence. Einstein says that space and time are curved and that freely falling particles choose shortest space-time intervals along the paths on which they travel. So it is absolutely true that gravity affects light. It affects light quite a bit, actually. I mean, if you go near a black hole, those pictures you see from black holes or in Interstellar, you see photons zooming around black holes multiple times before they escape. Having said all that, the actual question, there is a feature of general relativity that in some sense, the time it takes light to travel near a gravitational field would be less than the time it takes to sort of zoom around the outside and be deflected. So that it is a way, if what you're asking is, can we think about the actual motion of photons in curved space-time by using something like the principle of least time? The answer is yes. Now, I'm saying all that in very vague, heavily footnoted language because time measured by what, etc. You have to like figure out what your clocks are, but roughly speaking, that's true. So for government work purposes, yeah, that's fine. Rasmus Kies Nierbeck says, are there any ways for amateurs to contribute to physics in the sense of citizen science? You know, amateurs, the point here being there's a lot of citizen science that people can do to help contribute to science in things like biology, anthropology, or whatever, paleontology, botany. Physics is harder. And so physics is harder. It really is. For a whole number of reasons. And it depends very much on the kind of physics you're talking about. You know, if you're talking about theoretical physics, you know, creating new theories of cosmology or fundamental particles, then it's really, really hard for the basic reason that you need a lot of background, right? You need to take years worth of courses to get the background necessary to do the work. Now, in this day and age, you could do that, right? You could buy the books or you could just take the online courses and you could educate yourself up. Gerard de Tufft, the Nobel Prize-winning physicist, has a website where he goes through the whole curriculum of what courses you would need to take. He's a little bit overly enthusiastic, maybe. He wants to train you up to be a Nobel Prize winner, but if you just want to make some contribution, it's less than that. But honestly, you know, even if you did that, which is really hard to do, but not being around the community of other physicists, not being in graduate school, having friends you could talk with about problems and so forth, makes it really, really hard to contribute to that kind of theoretical physics at a useful level. There are other areas of physics, right? There's more experimental areas, etc. It is conceivable to me that citizens who are not professionals with less training than a PhD could contribute to those areas, but honestly, I don't know. It's not my thing, right? So I'm not an expert. Once you move into astrophysics, it becomes more possible. I mean, there are citizen science projects that, you know, monitor the sky for different things or do radio telescope kind of science. Again, I am not an expert. Sorry about that, but it is possible in principle. I think the overall lesson is that citizen science is great. And if you're interested in that, you should look into it. But it would be a mistake to be too devoted ahead of time to what kind of science you want to do. I mean, after all, if your interest is literally in doing citizen science rather than simply learning science, everyone is welcome to learn whatever science they want. But if you want to contribute to it, then given that motivation, you really should take into account where can you make the most interesting contribution. And that might not be in physics. So that would be my not very helpful, but hopefully correct advice. Thierry Leroux-Paquette says, when we do the double slit experiment to show the wave-particle property of an electron, how can we maintain the electron in a superposition state while its own gravity should interact with the surroundings and then decohere? And I'm going to combine this with the next question, which is Martin Kumber saying, something deeply hidden is one of the few popular science books I was able to read end to end. However, I struggle with the concept of decoherence. In particular, why doesn't everything become entangled by extension to everything else? And would this extended entanglement happen at the speed of light? So both of these questions are about the process of decoherence. The idea being, when you have a quantum system that is in some kind of superposition, when it interacts in a particular way with the external world, it becomes entangled with that external world, and that is going to lead to this phenomenon of decoherence. Decoherence simply is a little quantum system in a superposition becoming entangled with its environment. So the important thing, and I know this is hard to get across at a popular level of discussion, but the important thing to keep in mind here is that decoherence happens because of interactions, physical interactions, governed by the laws of physics, nothing weird or spooky. But not every interaction leads to decoherence. Decoherence happens specifically with the kinds of interactions that are affecting the quantum system differently depending on which part of the quantum superposition it's in, okay? So let's say that you have an electron or some other particle, a neutron. Electrically, I keep saying electrons when I talk about measuring the spin of particles. You shouldn't actually talk about electrons because they're electrically charged and it's hard to measure their spin directly. Neutral particles are easier because they're not being affected by the stray electromagnetic fields. Anyway, let's say we have a neutron. We're going to measure its spin, okay? You can do that, put it through a magnetic field. Spin up will be deflected one way. Spin down will be deflected the other way. The point is that in the initial state, if the neutron starts in a superposition of spin up and spin down, if I just take the neutron, in a box and I move it, I'm interacting with it, right? I'm moving the neutron from one place to another. But I'm interacting with the spin up part and the spin down part in exactly the same way. The fact that I'm moving the center of mass of the neutron is completely irrelevant to the different spin parts of the wave function of the electron. So that's not decoherence. That is not becoming entangled with the neutron. It's just moving it. It's interacting with it, but not becoming entangled. That's why you have to do all this work to measure the spin of the neutron by throwing it through a distorted magnetic field and watching it be deflected one way or the other, and then detecting it on the other side. You have to specifically interact with it in a way that interacts differently with the spin up part and the spin down part. That's what the magnetic field will do. Likewise, with the electron going through the double slit, it interacts with the slits, but it does not become entangled with them in different ways. Now, you ask specifically, Thierry, about gravity, and this becomes a subtle question, actually. Electrons or whatever, they're coupled to gravity. They're coupled to photons, right? Electromagnetism also. So if the electron passes through the slits and bumps into them with enough oomph, it can shake loose a few gravitons, or a few photons for that matter, and that could lead to decoherence. So it becomes a quantitative question. And in fact, you need to shake it pretty hard to decohere in that way. So the numbers simply tell you that even though the electron is dispersed by the slits it goes through, diffracted, it's actually not becoming entangled with them in any substantial way. Philip Lacasius says, after reading your latest preprint on Mad Dog Everettianism, I'm wondering what your philosophical motivation for pursuing this paradigm is. Is it maybe some kinds of Occam's razor philosophy that the most simple theory is the one that is most likely true? Or are there further reasons one might feel that other approaches are epistemologically less promising approaches? So I think it's both. So what Philip is referring to is, I wrote a paper a couple years ago with Ashmeet Singh called Mad Dog Everettianism. So Everettian quantum mechanics says the world is described by a wave function that evolves with time according to the Schrodinger equation. But usually when people do physics, they not only say there's a wave function, but they tell you something about the wave function. It's a function of position or of momentum or of quantum fields or whatever. And that gives you an enormous amount of extra structure you can use to probe the theory, to describe it, etc. The Mad Dog Everettianism says that wave function is just a vector in Hilbert space, okay? It's not a function of anything. The idea that the wave function, that the state vector, if you want to call it that, should be thought of as a wave function of something, should be an emergent phenomenon in some approximation at a coarse-grained level. That's the Mad Dog idea. And so in other words, you're removing even some of the very minimal ingredients that Everettian quantum mechanics typically helps itself to when describing the world. And you say all you have is a vector evolving according to the Schrodinger equation, and everything else should be emergent. That's the idea. So it's the most minimal approach you can have. And so I recently wrote another paper, Reality as a Vector in Hilbert Space. You can find it. And it is kind of a restatement of that idea, but this one is more aimed at philosophers. It was an essay that I wrote for an invited collection of essays on the fundamental ontology of quantum mechanics. And so rather than going through the equations, there were some equations in there, but mostly I sort of defended the approach because it was for philosophers more than physicists. And part of the motivation is exactly like you say, Occam's razor. If you have multiple theories that explain the same phenomena, the simplest one is a good bet to put most of your credence on until you know better. But also, I think it's the natural implication of being Everettian at all. I try to make the point that there's a big difference between living in a Hilbert space that is infinite dimensional and finite dimensional. If you are in an infinite dimensional, there's subtleties here that I can't go into now between there's different levels of infinity, countable and uncountable, et cetera. Okay. But in typical quantum field theory, you need to be given more information than just the wave function. You need to be given what are the observables of your theory. Okay. But I think that because of gravity, we don't have an infinite number of dimensions in Hilbert space, and then you're not given the observables. The observables are just all the observables. They're automatic. There's no extra information being attached to your theory. And in that case, I think you have no choice but to take this Mad Dog Everettian approach. So I think it's both simpler and inevitable if you're going to be Everettian at all in the real world. That would be my answer. George Aston says, could you take a guess at what might be needed to be discovered to get us one step closer to inertia, negation, or dampening technology as seen in Star Trek? And could the mechanisms behind inertia negation potentially offer an alternative idea to dark matter for why spiral galaxies don't spin apart? No, I don't think there is any such thing as inertia negation or dampening. And I don't think there's any such technology out there to be discovered. In fact, I did a Twitter poll the other day, a few months ago, actually. When hundreds of years have passed and humanity is, flying in spaceships all the time, and they have nostalgia night and they're looking at old science fiction movies from the 20th and 21st centuries, what will be the most annoying thing to them? The answer is clearly artificial gravity. Because there's no way to make artificial gravity except by spinning, something like that. There is just no known physics that would make that happen. And furthermore, things are much more interesting when you take into account the reality of the fact that you'd be in free fall most of the time in a spaceship, or you'd be pushed around by the acceleration. Okay, those are the only two choices. And that's kind of interesting, and it's narratively interesting. It does cost more money maybe to do the special effects, but the idea that on Star Trek we're just sitting on the bridge as if we're in Earth regular gravity, but we're moving forward is just crazy. It's just lazy. It's just nothing to do with what future physics is going to let us do. They do it. We all know why they do it. It's both sort of easier for the budget for the show, but also it's familiar. Right? It's easy because we're actually sitting on chairs on the ground to imagine that in spaceships, the same thing will be happening, right? Not because it's true and not because we have any prospect for technology in those directions, just because it's familiar. And, if you have enough unfamiliar things like tribbles and Vulcans, why make things even weirder? That's the basic idea. It's not because there's any hope for such technologies to really exist. I mean, there's other things you can do to sort of fake it. You could put magnets on yourself or something like that, but it's not inertia negation. There is no such thing. Eric King says, I am struck by the influence one's native language has on how they view and understand the world around them. My question to you is, how much do you think the language we use to describe science might affect our ability to really understand it? Do you ever feel that language we use to describe, for instance, quantum mechanics is holding us back from truly understanding it? I want to say yes and no. If you listen to the podcast I just released with Dean Buonamano, we talked about my half-baked idea that the human thinking, human cognition has undergone some sort of phase transition where we can manipulate symbols and reason symbolically and algorithmically, so we become kind of Turing machine capable. And at that point, even though your natural language does hold you back, it is a handicap that we can overcome, right? We can think our way out of that. Sure, I think that not only language, but just our intuition of the world is an enormous barrier to understanding quantum mechanics and other parts of theoretical physics at a deep level. We're just not trained to think that way or to reason that way or to conceptualize that way. And language is absolutely a part of it. But I don't think it holds us back in any fundamental way. I think it just makes it harder for us to do, right? It's not like a speed of light barrier. It's just like a hill we got to climb. And I think that, some of us are trying to climb it. Jessica Wolin says, I just read City by Clifford Simek. Have you read it? It was written in the late 1940s, and he describes what sounds like multiverses. Was that concept a thing in physics by then? So I haven't read it, but I thought it'd be fun to answer the question because I want to say I don't know whether that was a thing in physics by then, the idea of the multiverse. Physicists are very bad in general at understanding their own history and the history of the ideas they talk about. My paying attention to physics didn't really start until I was a kid in the 1970s and then a student in the 1980s. And the idea of the multiverse in the 1980s was just becoming popular in physics. And it was a combination of things. It was inflationary cosmology, gave us a mechanism for potentially creating a multiverse. The anthropic principle, trying to understand the cosmological constant, gave us a motivation for wanting there to be a multiverse. And the landscape in string theory was the idea that there could be different laws of physics in different parts of the multiverse. So that sort of gave us a mechanism for solving the cosmological constant problem coupled with inflation, et cetera. So this whole stew of ideas really made people think much more carefully about the multiverse in the 1980s and 90s. But you notice that all of these are driven by other ideas. So it's not, I've said this before, I'll keep saying it again, it was not that physicists in the 80s or 90s said, wow, like the multiverse, wouldn't that be cool? Like no one ever said that. You were forced into thinking about it by other ideas, and then you try to take it seriously. So, of course, Everett and the many worlds interpretation came in 1950s, but he didn't even call it the many worlds interpretation. That wasn't a label that got put on the theory until 1970 by Bryce DeWitt. So I have no idea what people were thinking about in the 1940s. I really don't. And I say this because I would like to. Like, it'd be very interesting for someone to do a careful historical analysis of the concept of the idea of the multiverse. Or maybe someone has and I just don't know about it. Sometimes I point to this paper written by Ludwig Boltzmann, back in 1895. Boltzmann was trying to answer the question, why was the entropy of the early universe low? Just like we were talking about, just like I'm still trying to answer that question, right? But over 100 years ago. And he was a smart guy. He, just to put it in context, Boltzmann and his friends came up with statistical mechanics and their definition of entropy and other things and their formulation of the second law back in the 1870s. And in the 1890s, for some reasons, which are a little bit obscure to me, sort of controversy flared up about it again. And Boltzmann was responding to criticisms by Zermelo. Zermelo later became famous as a pure mathematician, set theory axioms, right? But he was criticizing Boltzmann. And Boltzmann sort of offered these different reasons why entropy might have been low in the early universe, the problem that we now know as the past hypothesis. And Boltzmann invented what we might call the multiverse and what we might call the anthropic principle. He said, well, if the universe was infinitely big, he didn't know about general relativity, the Big Bang, or anything like that. So a static, eternal, infinitely big universe filled with gas and dust and particles just running around bumping into each other. Most of the time, in most of the places, it would be in thermal equilibrium. But occasionally there would be fluctuations. And the fluctuations would, as Boltzmann says, sometimes, because you have infinitely long to wait, sometimes the fluctuation would be so big as to create our universe, or at least our galaxy. He didn't know there were other galaxies, right? There's a lot of things he didn't know in 1895. And so Boltzmann says, look, in most of this huge collection, we're in thermal equilibrium and therefore dead. You can't have life in thermal equilibrium. But in these little pockets where you randomly fluctuate into low entropy states, that's where you can have life. And maybe that's us. Maybe that's what we do. And this would happen many times in many places. So it's both the multiverse and the anthropic principle, because he's saying we're not going to find ourselves in the dead places that are in thermal equilibrium. Now, number one, I don't know whether even that analysis is correct because he was kind of ignoring gravity. So I don't know that things would actually just keep bumping into each other over and over again. I suspect that what would happen in that scenario is gravitational instability and lumpy regions would just absorb all of the matter and it would sit there and empty out in between on progressively larger scales as time went on forever. So it would not remain uniformly distributed. Gravity is a tricky thing when it comes to entropy. But the other thing was, of course, his scenario is entirely 100% a target of the Boltzmann brane problem. And this was pointed out years later by Eddington, Arthur Eddington in the 1930s, who pointed out, look, if that were the world, randomly fluctuating, then we would expect to live in the smallest possible fluctuation. And what Eddington said was it would just be one mathematical physicist. That's all you would need, because he was a mathematical physicist. So I don't know. I don't know whether anyone back then used the word multiverse or anything like that. I don't know whether these speculations by Eddington and others had any impact on Clifford Simak. I just don't know. I mean, certainly science fiction over the course of the 20th century had a lot of fun with alternate timelines and alternate histories and things like that, but I don't know the origin of it. Andrew Vernon Smith says, are there scientific studies ongoing concerning where quantum physics and neurobiology or psychology merge, where choices consciously made in a human brain and observations deliberately collected by scientific instruments each collapse the wave function respectively at the choice made and state observed? I am not sure what exactly you have in mind by that last part of the sentence. To my mind, wave functions collapse when quantum systems decohere, when they become entangled with their environment. It could be, so the question is, how does that happen? Typically, we talked about the neutron going through the magnetic field, but you still need the neutron to interact with something. And typically, decoherence happens when you take that quantum superposition and you amplify it to something macroscopic, right? So people in quantum mechanics talk about pointer states of macroscopic systems when you literally have a little dial with a pointer on it saying, oh, the neutron went up or the neutron went down. And then photons will interact with that pointer differently, photons in the environment, and that causes decoherence. So a human choice, as I've said in Something Deeply Hidden and elsewhere, there's nothing about choices that collapse the wave function except when a choice depends on some quantum event in your brain. So, some chemical reaction happened or didn't happen because of quantum mechanics. And therefore, in one branch of the wave function, you had pizza and the other you had Chinese food, right? So that would count as decoherence. But you don't know. You don't know when you make a decision whether or not it depended on some quantum event in your brain, and typically it doesn't. Typically it's entirely classical. So there's no usual strong connection between making decisions and branching the wave function. There is a question you can ask about, is there any way in which the brain is explicitly depending on the rules of quantum mechanics? That is to say, not just obeying the rules of classical mechanics. Very famously, Roger Penrose and others have thought about ways that could be true. There's not a lot of support for those ideas in the physics community, but you never know. There are experiments going on. Maybe they'll find it someday. There is an idea due to Matthew Fisher, who is a condensed matter physicist at UC Santa Barbara, at the KITP, the Kavli Institute for Theoretical Physics in Santa Barbara. His idea, which actually I'm very, very fond of because I totally had this idea myself, but I didn't know enough about either quantum mechanics or condensed matter physics to make it real, and Matthew did, so he made it real. The idea is that you can have elements, atoms in your brain that are part of neurons whose energy can depend on whether the nuclei of the atoms are entangled in different ways. For some reason, it's phosphorus, I think, that Matthew Fisher pointed at as something that maybe could be relevant. So you need to shield it from a million other different forces, and that's exactly why I didn't have myself the knowledge to do this well. But he suggests, he hypothesizes, that there are conditions where neurons in the brain could have their energies dependent on quantum entanglement. Now, that has nothing to do with branching the wave function or consciousness or anything like that. But it is possible, just as it's possible that entanglement is useful in photosynthesis, it's possible that quantum effects are important in the brain. I think that's something we're still studying right now. Adam C. says, I currently find the terms populism or populist, anti-democratic, and elitist. The Google definition is a politician who strives to appeal to ordinary people who feel that their concerns are disregarded by established elite groups. To me, this sounds like a definition of democracy. Shouldn't all political candidates in a democracy strive for this ideal? Well, yeah, I mean, words like populism and populist are contentious. Different people will apply them in different ways. And I think that the Google definition you have there is fine, but the important part of it is not just doing what the people want. It's specifically this contrast being set up between ordinary people and elite groups, right? That's really where that's usually what is being implied by the label populist. And that sounds fair enough, right? Ordinary people, elite groups, which side are you going to be on? But if you go back into the very early days of the podcast, I interviewed Yasha Monk about liberal democracy and populism and things like that. And the case he makes, which I think is at least plausible, is that in practice, all of the effort is going into defining what you mean by the ordinary people, right? If you think about the actual populists that have been either self-identified or externally identified as populists, they very, very often get their oomph by defining the ordinary people in contrast, not with the elites, but with some other outsiders, right? Here's the in-group, here's the outside group. It could be foreigners, it could be minority groups within society, or whatever. So in practice, the theory goes, populism is really about dividing people rather than uniting people. And of course, I do actually think that there's a real problem in modern democracy with responsiveness to people on the part of the elites. I'm not quite sure how to deal with that, but I also think there's an absolutely very, very real danger in demonizing the other, whether it's foreigners or minority members or whatever. And that's the danger in my mind to populism. Very, very often, it's a step towards right-out authoritarianism, right? You claim to be the voice of the people, you repress other voices, and then you abrogate power to yourself. That's something that happens over and over again. There's no doubt. It's something we have to watch out for. Anders Hector says, in the big picture and in the interview with Netta Engelhardt, you describe conservation of information as the state of a system and what we know about it, but that is sort of a state of affairs of the system. It's aboutness of the state. How about the state as such? Would you say that information only exists in relation to thinking beings, or does it have an existence independent of any biology? So, as usual, I can't exactly remember what I say at every time. So the information, when we talk about conservation of information, we are not talking about what we know about it in any sense whatsoever. Information is conserved whether or not we know about it. The information in the sense of conservation of information is, you can think of it if you want, as a counterfactual idea. All of the information you would need to know to follow the dynamics of the system, to predict the dynamics of the system under the laws of physics. So it's really complete information that you would need, complete information that is there in the system, whether you have it or not, okay? So Laplace's demon has access to all the information, but you don't. That's okay. The information is still there. That's the information that is conserved. So it has nothing to do with living beings, biology, anything like that. In that sense, of course, the word information, like many other words, is used in different senses by different people at different times, but that's what it means in that context. Chris Fotash says, in the first Mindscape episode I listened to a couple of years ago, you spoke about how the largest possible number allowed by some physics law, I think you referred to Hilbert space, and it was something like 10 to the power of a few hundreds. If my memory is right, the question would be, is there a hard physical value to infinity? So to refresh your memory, it's not the maximum number. It's not the biggest number that we're talking about here. What we're talking about is the size of Hilbert space. So Hilbert space is, David Hilbert is the mathematician who it's named after. Hilbert space is a particular kind of vector space where you can take dot products, but instead of being two-dimensional or three-dimensional, it's a vector space that is some number of dimensions. There's different numbers of Hilbert spaces. You can have a two-dimensional Hilbert space, three-dimensional, four-dimensional, etc. Quantum mechanics says that the state of the universe is a vector in Hilbert space. I referred to my paper earlier called Reality as a Vector in Hilbert Space. And the question is, how many dimensions does Hilbert space have? Does the Hilbert space describing the universe have? And I think, some people think, that our observable universe can be described as a vector or a matrix in a finite dimensional Hilbert space, but a big dimension. The dimensionality we throw around is something like 10 to the power 10 to the power 120. That's the number that you're thinking of, probably. But that's not a physical limit to infinity. So it's the number of different possible things that can happen in the world, very, very roughly speaking, number of different states the universe can be in, number of different distinguishable states the universe can be in some sense. But I can write down numbers much bigger than that. If, I can write down the number 10 to the power 10 to the 10 to the 10 to the 10. Way bigger than the dimensionality of Hilbert space. I could never write down all the zeros in that number. There's not enough atoms in the universe to do it. But I can imagine those numbers. So all of which is to say, there is a very interesting question about the foundations of mathematics, whether or not you need infinity. There was a movement, I think in the early 20th century, of finitism. Maybe it was the late 19th century. To really see whether or not we could just get rid of, like, all of the difficulties in the philosophy of math and the foundations of set theory and all these things deal with infinities in some way. Infinity is really where you get into trouble. And it's easy to imagine infinity, right? You just say, well, I have 1 and 2 and 3 and 4 and 5, and I keep going. I never stop. So there's an infinite number of whole numbers. But maybe you don't need to. And maybe there is a relationship between that idea and physics. There's no necessary relationship, but maybe the physical world doesn't require an infinite number of numbers or a well-established notion of infinity to make sense of it. Honestly, I don't know. That's beyond my pay grade. Even in Hilbert space, even if there are an infinite number of distinguishable states, orthogonal states, perpendicular states, there's still an infinite number of vectors. They're just almost aligned with each other, most of them. So there's an infinite number of states the universe could be in. So I really don't know what to make of that. I'm not the person to ask. Sorry about that. Stephen Bernard says, topics and questions at the bleeding edge of physics invoke hypotheses that are either in principle or in any reasonable foreseeable practice unobservable. My philosophical question is, what is your opinion of the epistemological weight of such hypotheses, and how much work can they be expected to do? Are they to be taken as seriously as experimentally falsifiable ones? Well, if you want a slightly more detailed answer, I did write a paper called Beyond Falsifiability, where I talked a little bit about this issue. I'm not especially an expert or interested in the philosophy of the practice of science. So I think these are interesting, important questions, but it's not my kind of specialty, my kind of expertise. So I can't really offer you a definitive answer here. But I think that what you can observe is overrated when it comes to judging scientific theories, because you can have unobservable things whose existence or absence affects how we think about observable things, right? So quarks are individually unobservable, but they affect how we think about observable things. Virtual particles are even more unobservable, but they play a role in explaining observable phenomena. So something like the multiverse, the cosmological multiverse, where you have regions of space very, very far away, where conditions are very, very different. Does the existence or non-existence of those other parts of the universe play a role in how we think about the observable universe? Well, if something like the cosmological constant, the vacuum energy of empty space, is not determined by some as yet unknown but perfectly deterministic laws of physics, and is instead just different from place to place in the multiverse, then our job as scientists is very different depending on those two options, right? What kind of ways you think about the cosmological constants does depend on that issue. Therefore, you need to take it epistemologically seriously, right? Even if you can't see them outside or not. In the case of the many worlds interpretation of quantum mechanics, the formalism says there are other worlds, other branches of the wave function where different experimental results happened. We'll never see them. But they play a role in the formalism that we have to explain what we do see. So I think that's a much better criterion to use than what you can directly see, falsify, etc. Remember, you don't falsify predictions. There are plenty of predictions that are completely unfalsifiable, but yet you believe them. You falsify theories. Once you can falsify a theory, then it's a good thing to think about it scientifically. But that theory might have specific predictions that are unfalsifiable. That shouldn't bother you at all. Andrew Vickerstaff says, what future discovery or observation would increase or decrease the credence of many worlds compared to other foundational theories of quantum mechanics? Right. So speaking of which, look, many worlds says there is a wave function or a state vector. It evolves all the time under the Schrodinger equation. So all you need to do to falsify the many worlds interpretation is to do an experiment where the wave function does not obey the Schrodinger equation. These experiments are ongoing. Roger Penrose makes predictions that we should see them, right? There's other theories of objective collapses that says we should see them. So that's just one way. Also, you could find evidence for dynamical variables other than the wave function, because those don't exist in many worlds. So there's plenty of ways in which you could experimentally do these things. They're hard experiments to do, and they may never converge on anything, but they're there in principle. If you care about the philosophy of it rather than the practice of it, there's zero question that many worlds is completely 100% super duper falsifiable. Victor Yakin says, can you envision a set of conditions for a simplified Laplace's demon experiment where many variables are controlled but with sufficient computing power and knowledge of initial conditions so we can accurately predict the actions of a human for a short period of time? No, I cannot. Humans are very, very complicated, and not only of order 100 billion neurons in our head, but of order hundreds of trillions of connections between those neurons. And neurons are not individually simple. Neurons are kind of complicated. So no, even measuring where all the different pieces are would be impossible, much less actually calculating what all those pieces would then do. So no worries about that in my mind. Carlos Nunez says, what do you think about the following moral realist argument? Morality concerns the well-being of conscious creatures, and if we want to maximize their well-being, we have to take into account the biological constraints of said creatures. That is to say that there are some moral facts about us humans and primates in general which result from our evolutionary history. So sorry, Carlos, but I don't think that's a very good argument at all. It is full of wild non sequiturs. Sorry about that. So morality concerns the well-being of conscious creatures. Sure. That's just a definition, right? I mean, that's just what you mean by the word morality. Like if there weren't any conscious creatures, there wouldn't be any morality. That's fine. But then you say, and if we want to maximize their well-being, well, wait, hold on. Who says that we want to maximize their well-being? That's not implicit in the definition of well-being or morality or anything else. That is one particular possible moral axiom that you might want to defend. Other people don't think that our job should be to maximize the well-being of conscious creatures. Maybe maximizing the overall well-being is something that would hurt some people really badly while it helps other people, and so they don't want to do that. I think personally, just the idea that there is something to maximize, that there is something called the aggregate well-being that we can measure and quantify is wildly wrong, personally. So that's just a leap that is completely impermissible. And then you say we have to take into account the biological constraints of said creatures. Sure. No one ever has argued that science has no impact on how we go about being moral. Like that would be a crazy argument. There's an argument that says that science doesn't determine morality, that morality is not part of science, but science describes the real world. If you want to be moral in the real world, you have to take science into account, obviously. And then you say, that is to say that there are some moral facts about humans which result from our evolutionary history. So no, that is not, sorry, that is not to say that. The idea that you have to take into account biological constraints does not lead clearly to there are moral facts that result from our evolutionary history. There's just a huge leap there. There are constraints, but they don't lead to moral facts. They don't tell you what is right and what's wrong. They tell you that if you know what is right and what is wrong from some other reasons, then you have to take into account biological constraints in achieving them, right? So it's just way more, let me back up a little bit. This is not hard. This is not controversial. Like no sensible person thinks that you can derive moral facts from pure logic. That you derive it from somewhere, maybe. Like I don't think you can derive them from anywhere in any objective way. But you need extra input somewhere. Like I had Russ Schaefer-Landau, who's one of the world's leading moral realists, on the podcast, and he thinks that it's our intuitions that give us some insight into what the moral facts are. But you have to get them from somewhere. They don't just appear from nowhere. In particular, I'm not going to go into particulars. You've heard me talk about this before. I wrote a book called The Big Picture where I talk about this, and I've written many blog posts. So those are my feelings personally. Michael Edelman says, several episodes back you said, half in jest, something like maybe game theory is just physics. Given all the mathematical patterns that pop up across all matter of systems and structures, do you think that tells us something interesting and deep about the way the universe is structured? Well, I can't say that I think that right now because I'm not sure or even especially confident that game theory is just physics. So what I meant by that statement was, game theory is a way of determining certain strategies for certain formal games under certain conditions, right? Like given certain payoff structures, what should individual actors in the game do? That's what game theory tells you how to do. What I meant by saying maybe it's just physics is that kind of optimization problem is something that we're familiar with from physics in other contexts. It's all the time happening that different physical systems optimize something. The principle of least action says that individual particles minimize their action. When you have statistical mechanics or thermodynamics, systems go to equilibrium where they maximize their entropy, things like that, right? So I'm just wondering out loud whether or not there is some more formal connection between these physical systems that we know optimize, maximize, minimize something, and the search for strategies in game theory. But I don't know that it's true, so I haven't done that yet. I'm thinking about it. I don't know. I would probably guess it's not true in a useful way. Like maybe there's some very formal analogy there, but I don't necessarily see that there's going to be some useful analogy. Those are a different thing. Okay, Brad Goldberg says, you often stress that in quantum field theory, fields represent a deeper, more complete concept than particles. However, standard first quantized string theory looks more like a theory of fundamental particles zipping around where subsystems are not arranged into a nearest neighbor structure. By analogy to quantum field theory and relativistic quantum mechanics, do you think that the string fields of string field theory are a relatively deeper, more comprehensive formalism of the theory than first quantized strings? So for those of you who are not experts, the idea here is the following. We know about quantum field theory. Quantum field theory is the best current empirically successful way we have of understanding the world around us, experimentally in physics and so forth. You need quantum field theory to have particles created and destroyed, obey the rules of relativity, all that stuff. So even though you might have thought back in the day, I don't know, in the 1920s, that you could make a theory of particles. Actually, Richard Feynman thought this in the 40s. But that's okay. You make hypotheses. It didn't work out. So Feynman was hoping that his little Feynman diagrams would enable us to get rid of quantum field theory. We could just talk about particles, right? To sum up the effect of an infinite number of particles, that's better than doing a field. That's what he thought. It doesn't really work that way. The truth is that the particles in Feynman diagrams are vibrations of quantum fields. Okay, the fields are more fundamental. Now, in string theory, as Brad says, the usual way that string theory is formulated is more like particles than fields. So you talk about individual vibrating strings, just like you would talk about individual particles, and you do Feynman diagrams with them, and that is your theory, okay? You might therefore, by analogy, say, well, what you really want is a string field, and maybe that would give you deeper insights into the dynamics or nature of string theory. And people have tried that. Ed Witten has made important contributions here. Murray Gell-Mann and Barton Spivak wrote papers about string field theory. But it's never really caught on in the same way that quantum field theory replaced point particles in some way. And honestly, Brad, I do not know enough about it to say why not. Again, people have tried, but it's just not really operationally panned out to be that useful or that insightful or whatever. Is that because it's not there? Is it because string theory really is a theory of individual strings rather than fields that are collections of strings? Or is it just we human beings haven't been smart enough to think about it in the right way? I really don't know. I did do a little bit of thinking about it. I thought about what you might call classical string theory, but I never wrote any paper or anything like that about it. It would certainly be mathematically complicated. So one of the possible options is people like me have tried it and thought about it and go, that's too complicated. I'm not going to think about it anymore. I have other things that I can think about. So I'm not a string theorist professionally, so I'm not really the one to ask, but my impression is working string theorists don't really think that much about string field theory, and I'm not exactly sure what reason they would give. Okay, now I'm going to combine two questions here. Greg says, special relativity says that the speed of light is invariant for all observers in inertial reference frames, but I'm confused about whether this is an assumption, an experimental result, a law of nature, or a logical consequence of other things we're sure of in physics. And Brian Carmody says, I understand that the speed that photons travel in a vacuum arises from the magnetic and electric constants, which are fundamental parameters of the universe. I also understand the geometric argument from special relativity that there must be a maximum speed at which things can travel. My question is, why is this maximum speed for everything also the exact speed at which electromagnetic waves propagate and not some other speed? Why is the speed of neutrinos, etc., seemingly limited by electromagnetic constraints? So both of these are about, what is the nature of the speed of light in modern physics? And so to Greg's question, it's actually kind of a nice framing of it. He says, I'm confused about whether this is an assumption, an experimental result, a law of nature, or a logical consequence of other things. And the answer is it's all of those. So the thing, I think that the hidden question that is being begged here is physics as we understand it, or as we will understand it or should understand it, some kind of axiomatic system where we start with the most foundational statements and then build everything on top of them, or not? And the answer is that for individual physical theories, you can very often write down a set of axioms and derive the theory from it for general relativity or special relativity or quantum field theory or whatever. But you can also very often write down an entirely different looking set of axioms and derive the same theory from it. And when that is possible to do, arguing over which are the right axioms or the right sort of foundational pieces for whatever you're trying to do is not always a useful use of your time, productive use of your time. In other words, I think that the right way to think about theories in physics is not as there's a foundational set of axioms and we derive everything from them. It's a little bit more holistic than that, right? There's a set of statements that are true, and they're all true. And it's not like some that are truer than others once you have a well-defined physical theory. And you can choose different ways that some of them can be derived from others, etc. But the whole thing fits together. It's more like a web than a hierarchy where you start with the bottom level and build everything on top of that bottom level. So the fact that the speed of light is invariant for all inertial observers, by the way, it's not inertial observers. It's just invariant, no matter what. You don't need to be in an inertial reference frame. The laws of physics are invariant for all inertial observers, is maybe what you have in mind. But the speed of light is just constant for everybody. So is that an assumption or a logical consequence of other things? Either way, you can do it either way. So I think it's a slight change of shift about how you think about the role of these sorts of statements. Is it an experimental result? Also, yes, it certainly is also an experimental result. And for Brian's question, what about the other things, right? Like gravitons and things like that. Why are they limited by the speed of light? I mean, I think that you're sort of, I can see in the way that you phrase the question, you're almost there. You're almost grasping it. The point is, there is a speed limit, right? That's the point of special relativity. There's a speed limit. There are light cones, as we call them. The fact that light, electromagnetic waves or photons or however you want to think about light, the fact that light happens to move at the speed limit is much, much less important than the fact that there is a speed limit. After all, light doesn't move at the speed limit if it's like moving through water or air or something like that. It only moves at the speed limit in vacuum. So what you have is a system where there is a speed limit, a maximum speed, a limiting velocity, and then you say, well, what kinds of things move at that velocity and which kinds of things move slower? And the answer is, from a particle point of view, massless particles move at that speed. Massive particles move slower than that. So really all you're asking is, why are photons massless? Just like gravitons are massless. And the answer is because of symmetries in the deep down laws of physics that give them their mass, or actually symmetries that prevent them from getting mass. It's a better way of saying it. And I can't give you an airtight argument for why massless particles move at the speed of light, but there's an intuitive argument for sort of why it makes sense. If you have a massive particle, you can always consider that particle in its rest frame, right? A particle that moves slower than the speed of light, you can always change your own speed, so you are at rest with respect to that particle. And then you can ask, how much energy does it have? And the answer is E equals mc squared. That's the energy in a particle in its rest frame. If it's moving faster, it's moving at a non-zero velocity, then it has more energy. That's kinetic energy as well as rest energy, right? But a particle that is at rest has a minimum energy. That's its rest energy. That's what the formula E equals mc squared tells you. And then the way to think about what mass is from this point of view is how much energy does a particle have when it's at rest, okay? So every particle that has a non-zero mass has to be able to be at rest to define that. And therefore, the other way around, every particle that can be at rest has a mass, and vice versa. And so the particles that can be at rest are the particles that have mass. If you always move at the speed of light, then you can never be at rest. By the definition, those are the rules of special relativity. Things that move at the speed of light always move at the speed of light. So things that move at the speed of light don't have a rest mass. Therefore, they are massless. That's what we say. They still have energy, but all their energy comes from their motion rather than from their rest mass. So hopefully that gives a little bit of intuition there. Alexander Freund says, in discussing entanglement, I've heard you refer to a degree or extent of entanglement. For example, that two particles are very entangled or slightly entangled. What exactly does this refer to? My basic intuition is that two particles are either entangled or they are not. Nope, that's a bad intuition to have. So think about, two particles that might be entangled. Let's say two particles that have a spin, right? So spin up or spin down. There's two particles. There's Alice's particle and Bob's particle. And if you think about how they're entangled, usually you're given an example something like you're in a superposition of both particles are spin up plus both particles are spin down, right? That's an entangled superposition such that if you measure the spin of one and it's up, you instantly know the other spin is up also. Sometimes, by the way, they're opposite, but it doesn't matter. It could be oppositely entangled or entangled in the same way so long as they're entangled. But that is a particular superposition, right? There's another state that the particles can be in where they're both just spin up, right? If both particles are just 100% spin up, that is not entangled. Even though they're related to each other, you don't learn anything about one particle by measuring the other one because you already knew that both particles were spin up. So if you measure one and see it spin up, you don't learn anything about the other one, okay? So that other superposition, up, up, plus down, down, that's maximally entangled because secretly what we're not telling you, but what is true is that Pythagoras' theorem is at work here, right? This superposition has coefficients. So it's A times both particles up plus B times both particles are down with the rule A squared plus B squared equals 1 because their squares need to sum to 1. That's Pythagoras' theorem. So it's really, if it's an equal superposition, it's 1 over the square root of 2 up, up plus 1 over the square root of 2 down, down. That gives you a unit vector. Whereas if you just have up, up, and nothing else, then it's 1 times up, up. And once you realize that, once you put back the numbers in that people like me usually hide from you in popular level discussions, you realize the numbers could be any two numbers whose squares add to 1. So the up, up could have a coefficient, the square root of 0.99, and the down, down could have a coefficient, the square root of 0.01, okay? That is a superposition, but it's almost the same as just having it all be up, up. So that is a slightly entangled superposition. If you went all the way, so it's only up, up, it's not entangled at all, and it becomes more and more entangled as the two terms up, up, and down, down go from being 1, 0 to being 1 over square root of 2, 1 over square root of 2. So you can have any amount of entanglement from 0 to maximal. Louis Waweru says, are life forms entropy-reducing systems? I'm tempted to say, have you ever met a life form? Most life forms I know are not entropy-reducing systems. No, in fact, every life form I know is not an entropy-reducing system. It's the other way around. Life forms are necessarily entropy-increasing systems if we include the entropy of everything, the entropy of the universe as a whole. What life forms do is they take in low entropy energy from the universe, whether it's sunlight for photosynthesis or food for animals or something like that, and they increase its entropy. They extract energy from it by degrading that energy, by converting that energy into waste heat with higher entropy. And that is how these organisms maintain themselves, repair themselves, metabolize, and do all the things that they do. So life is just another way to increase the entropy of the universe from some point of view. James Maddox says the Planck length and Planck time are supposed to represent a scale where quantum gravity becomes important. I've also heard that they may represent the quanta of space and time and the size of the smallest black hole. But aren't they just constructed by combining constants of nature until the units work out? How sure are we that these exact values have physical significance? I think it's a really good question because the answer is we're a little bit less sure than you might think from what people say. So on the one hand, you're completely correct that these units, Planck length, etc., are just constructed from other laws of physics, right? It's numerology in some sense. But on the other hand, physicists are trained to sort of have expectations about when different effects become important. When you travel near the speed of light, you expect special relativity to become important. When the gravitational force, the gravitational constant is similar in magnitude to other things going on in your system, you might expect gravity to become important. When the action of your system is close to h bar, Planck's constant, you might expect quantum mechanics to become important, et cetera, and so on. So the fact that when people say quantum gravity becomes important at the Planck scale, that is the expectation of physicists. It's just a rough back of the envelope kind of expectation. In fact, in string theory, there is something called the string scale, which is not the same as the Planck scale, but is close. It is a dimensionless number times the Planck scale. And so in string theory, stringy effects become important a little bit earlier than the Planck scale that you might hit. So the point is, we don't think we know the once and for all theory of quantum gravity. But when we do, we expect that intrinsically quantum gravitational effects will become important at around the Planck scale. The specific theory might tell us that the actual time or regime or parameters for which they become important is a little bit different. If it were very different, that would require some extra physical mechanism, right? And indeed, large extra dimensions of space-time would provide such a mechanism. Gravity can become much important way before what we know as the Planck scale. So we don't know. If there are, we haven't found any large extra dimensions, so that's still, the Planck scale is still our best bet. Ludwig Schubert says, Wikipedia tells me that we are in the middle of the stelliferous era, a time period in the existence of the universe during which new stars are still being formed. Does this mean the sun burning out shouldn't worry us too much because we can expect new stars to form for another 1 to 100 trillion years? That would sound like really good news to me, suggesting most of the useful lifespan of the universe is still ahead of us. Well, Ludwig, I don't know why you're worried. Even if it were just the sun, it would still be a few billion more years. So I'm not quite sure what exactly your anxiety is coming from. Certainly you and I will not be around to worry about these things. And now you might, I get it. I mean, you might want life to exist for as long as possible. But, you know, let's be a little bit realistic here. We don't know what form life is going to be in or take or adopt even 1,000,000 years from now, much less 1,000,000,000 or 1,000,000,000,000 years from now. So, I mean, to actually answer your question, yes, stars are still forming. In some galaxies, star formation is more or less over. Roughly speaking, elliptical galaxies are done forming stars. That's not 100% true because stars explode and put out gas and dust into the regime, into the space around them, and then more stars can form from that. But spiral galaxies are the ones that still have ambient interstellar gas and dust, and you can still form more stars, whereas ellipticals have sort of used up all their gas and dust. But there's a cycle, like you say. Stars explode, they expel gas and dust into the interstellar medium, and you can form more stars. So yes, there will be a long time, we believe, in front of us in the future where more stars are still formed. Now, there are details, like even if you want to say, well, forget about technology and civilizations and stuff like that, will the next generation of stars be appropriate for forming life around them? So will the next generation of stars have the same kind of solar systems and planets that current stars have? I don't know. I mean, probably, but honestly, I don't know. So I think that it's certainly plausible to me that stars like the sun, solar systems like ours, will form on into the future for a long time, but I actually don't know. Like maybe they're all much lower mass stars. Maybe they burn a long time, but don't burn very brightly. I just don't know. My point is only that there are a lot of details that go into these kinds of questions. They're not easy ones to answer. Peter Bamber says, from the outside, the United States looks like a strange country with an insane attitudes to guns in many states and many other unique things, baseball. Is American exceptionalism as clear from within as it is from without, and how do you feel about it? So I think the phrase American exceptionalism isn't the right one to use here. You mean something like American particularity or something like that, strangeness, uniqueness. Exceptionalism is a phrase used by pro-American people to say that America is better than everywhere else. And that's one issue. A different issue is America forgetting about better or worse? Is it just different from everywhere else? And these are always hard questions to answer because I think that almost every country is unique in its own ways, right? The United States did have a unique position in the world for the last roughly century, okay? Maybe not entirely a century, of being the most powerful, technologically advanced, and richest country, okay? A century is not that long, historically speaking, and there's zero guarantee that that kind of condition extends into the future, as we all know. So China is an obvious example of a country that very well could overtake the United States in technology, wealth, all those things. But being in that position does, allow a country to start patting itself on the back and treating itself as special. I'm sure the countries throughout history have done that. I'm sure the Roman Empire did that back in the Roman Empire ruling the world days. I'm sure China did that in its empire days, etc. So, I don't know. I'm not that surprised or struck by it. The other thing is that is worth mentioning is that America is big as a country. We literally have two borders, one with Mexico, one with Canada, and many people in the United States don't live anywhere near one of those borders. And the Canadian border, which is much longer, is with a country that also speaks English and came from sort of the same predecessors, colonial past as we did. So unlike people in many other countries, we're not constantly visiting other countries, constantly being exposed to cultures from other countries, constantly sharing resources and things like that. There's no European Union in North America, that kind of thing. So it's a different kind of expectation. There's plenty of Americans who have never left America or don't really want to, whereas there's not that many French or German people. At least the fraction is smaller, let's put it that way. So if you live in Europe, then, experiencing other countries and getting to know them is just much more part of your everyday expectation than if you live in America. And, none of this is right or wrong. Every country has its good parts, its bad parts, etc. It's just hard to judge other countries or your own country objectively. So I don't like to go too far in these comparisons. Sandro Stuckey says, my friend Max and I thoroughly enjoyed your discussion with Justin Clark Doan as it sparked an interesting discussion among us and our colleagues. During the discussion, Max raised the following point. If we can be pluralists about mathematical and moral theories and truths, can we be pluralists about realism itself? Or is there some objectively unique and true meaning of the word real? So I can only give you my opinion here. We don't know. These are the kinds of questions where, I could be very, very wrong at the deepest level, but I don't think it's analogous, actually. I am a reality realist. I think that whatever there is, whatever the real world is, there is something that it is, right? There's something that it is uniquely the real world. Now, we might eventually find out that there are different ways of talking about the real world. I mean, there clearly are different ways of talking about the real world at different levels of approximation, right? There are emergent higher level descriptions. There might even be different ways of talking about the real world at the single fundamental level. As some kind of analogy, in classical mechanics, those of you who are either physics educated or have taken my big pictures in the universe videos, you can think about just classical mechanics in a Newtonian language, where there are particles and they're being pushed around by forces. Or you can think about it in a Hamiltonian language, where momentum is just as real and fundamental as position is. It's not just derived, it's a separate independent quantity. Or you can think about it from a Lagrangian point of view, where you have the action, which is defined over the whole trajectory of the particle. And that is what gives you the motion of the particle. So ontologically, these sound like very different choices for what is real and what is fundamental, but they describe exactly the same physical theory. So I'm very open to that. I'm very open to the possibility that reality can be described at the most fundamental level in very different ways. But I don't even know what it would mean to say that reality is different. Then what? Then, I think we all live in the same reality. I think there is a unique world in which we live. I think we discover things about it in a very contingent, slow, approximate, fallible way. But I think that there is a reality there. I know that not everyone agrees with that, but I'm honestly not even clear what it could mean for that not to be true. We seem to share the same world in a very real way. So that's where I'm voting until there's good evidence otherwise. Daniela Cortesi says, could it be that libertarian free will appears to be incompatible with the laws of physics because it cannot be captured by mathematics? I mean, suppose that it is real. How would we express it in the equations of physics? So I think there's something that you're getting your finger on that I'm very sympathetic with here. So the lack of libertarian free will can be re-expressed as saying that human beings just obey the laws of physics. Okay, we have no way of being a law unto ourselves. Just being a person and an agent does not give us in any sense the ability to override what the rules of the core theory tell us that our atoms and particles should be doing. That's non-libertarian free will. So what is the alternative? I mean, we call it libertarian free will, but what does it mean really? Like, what would it be? Does it mean there are other equations that govern the choices people make, but they're not the laws of physics? Does it mean that there are no equations at all? And what would that mean? Like, even if human behavior was unpredictable, presumably you could still come up with a probability measure and say, well, there's a probability that certain things happen and a probability that they don't. Certain actions are taken by certain agents and conscious creatures. After all, that's just what we do in quantum mechanics, right? We still call it a law of physics. So I'm a little concerned that there isn't any good definition of what you would mean by libertarian free will. But it doesn't bother me that much because I don't believe in libertarian free will, so I'm kind of not worried about this. It reminds me of when we had, back in 2012, when I organized the Moving Naturalism Forward workshop. And so the idea was get a bunch of naturalists in the same room, and rather than debating with theists or religious people, try to work on the questions that we had amongst ourselves, which are multiple. And people got stuck right at the beginning trying to define what naturalism is. And I was like, don't spend our time doing that, because it is hard to define, but it's only hard to define because you don't know what supernaturalism is. Like, naturalism makes perfect sense. There are laws of physics and there's stuff and it obeys the laws of physics. That's naturalism, right? Supernaturalism is hard to define, but who cares? We're naturalists. We don't need to worry about that. I feel the same way about libertarian free will. Okay, we have a whole bunch of questions that I'm grouping together. So let me just read all of these questions and then riff on what the answers are. Deepthi Amarasurya says, how do conservation laws fit into the many worlds interpretation? Rob Graber says, how does an Everett many worlds interpretation reconcile with the conservation of matter and energy? Do matter and energy multiply to fill each new world? Douglas Long says, why is the creation of a new world not a violation of information traveling faster than light? Joseph Tongretti says, it would seem according to the many worlds interpretation that our world is not just the splitter from which other worlds emerge, but also a continuous splittee. Can our world simultaneously split from more than one trunk world? And can we deduce that there was an original trunk version of the universe from which all the other worlds split? Suraj Rajan says, can you clarify the many worlds explanation for the double slit experiment? I got a bit confused after you mentioned in the last AMA about both being in the same branch of the wave function. And Jeff B. finally says, the branching of the wave function makes sense to me when talking about a simple two-state system like spin, but there is a conceptual challenge extending this to position measurements. In order to make things make sense, like the double slit experiment, we need to think of the wave function as a superposition of each possible position of the particle. But is there a philosophical explanation for why the wave function chooses to decompose itself in this way? So specifically as a superposition of position rather than different kinds of things. Okay, so these are not all the same questions, certainly, but they're all in the world, if you will, of many worlds and branching and what defines branches and how does that remain compatible with things we know like conservation laws. So let me just discuss a little bit what is meant by the branching, and then we can go into the conservation laws. So remember, as we just discussed a little bit ago, in many worlds, the fundamental way we describe the world is as a vector. It's a vector in some super duper high dimensional vector space called Hilbert space, okay? And what is really happening when you branch the wave function is that you can always write a vector as the sum of two other vectors, right? If I ever just draw an arrow in some direction, I can always decompose that arrow into the sum of two arrows 45 degrees away from it, right? 45 degrees on either side. And each of the shorter arrows has 1 over the square root of 2 the length of the longer one, and I can add them together to get the longer one. And in a much higher dimensional vector space, I can do that over and over and over again. So I can write any vector as the sum of a huge number of other vectors, each one of which is very tiny, right? So I can make a big vector by adding up little vectors to get the big one. So that's all just math. That's all just formalism. There's no physical content there. In many worlds, the specific thing that is happening is that some vectors are preferred over others. And the reason why is because we make this division of the physical stuff of the world into the systems we care about and the environment. The environment is everything we don't care about, okay? And then the environment is constantly monitoring the system. The photons or the box of gas, the gas in the box that we're dealing with are constantly bumping into the system. And in some sense becoming entangled with it if the system is in a superposition. If it's a macroscopic system in a superposition, it entangles with the environment very quickly. That's decoherence. That's what we talked about, okay? So what we call branches of the wave function is a long lead up to saying what we call branches of the wave function are those little vectors that we add together to make the big vector, which is the wave function of the universe, where the little vectors are ones that don't become entangled anymore with the environment. So the classic example here is Schrodinger's cat, right? If you have Schrodinger's cat, you have a cat that is in a superposition of awake and asleep, I like to put it. But what really matters is not whether the cat is awake and asleep or alive and dead. What matters is the cat is in a superposition of two different macroscopic configurations of the cat. It could be Schrodinger's rock or Schrodinger's hat or whatever, as long as you put it macroscopically in a superposition of two different positions. Because then what happens is those two parts of the superposition interact differently with photons. Some photons will hit the cat if it's in one place, but not in the other place. That's what causes decoherence. Wave function branches, you get two branches. But then crucially, super duper crucially, once that happens, once you have just one branch, once you're considering what happens just on one branch, you have a cat, it's in some location. Photons are still hitting it, right? But they're not entangling with it because on that branch, the cat is in one particular configuration, one particular position. That's what's called a pointer state. And the photons just keep hitting it and bouncing off or being absorbed or whatever, but they're not entangling it. They're not interacting with it differently depending on different parts of the quantum wave function of the cat, okay? So that's why certain vectors, certain quantum states are preferred because they remain robust under being monitored by the environment. Okay, I hope that is all useful information. Now let's try to use it to answer some of these questions. So as far as conservation laws, matter, energy, etc., I did just write a paper on this and a blog post explaining the paper. So I encourage you to dig up on my blog. I have not been blogging very much, so it's not hard to find. Go to the blog, preposterousuniverse.com/blog, and you'll find a blog post explaining how energy conservation works in many worlds. And the answer is it works pretty well, but not exactly. And this is sort of an interesting, subtle thing because this speaks to the other question about conservation laws. Something like electric charge turns out to be different than energy in many worlds. And the reason why is because electric charge is something that the universe can be an exact state of. So in fact, it probably is in a state of zero electric charge. If you were going to guess, right, that would be the easiest guess. Zero total electric charge. Plenty of positive charges, plenty of negative charges, but they come in equal amounts, okay? And that's fine. Nothing wrong with that. Things go on. But with energy, energy is what tells us how the universe evolves with time. And the specific way quantum mechanics works, the specific way the specific way the Schrodinger equation works in quantum mechanics is that if you put a quantum system in a state of exact energy, so you know precisely what the energy is, and it's not a combination of different energies, it's one's precise value, then the system doesn't evolve at all. Nothing happens. All of the time evolution in quantum mechanics happens because real physical systems are superpositions of systems with slightly different energies. And those slightly different energy subsystems evolve at slightly different frequencies that beat against each other to constructively interfere, destructively interfere, etc. And all motion and all time evolution in the world is that in quantum mechanics. So unlike electric charge, energy is something where we can't be in an exact value of the energy. We have to be in a superposition. And what that means, as I explained in the blog post, which is based on a paper I wrote with Jackie Laudman, what that means is that the particular set of energies that go into our universe can change with time. They don't change from one set of energies to a completely different set, but you can narrow down, right? So you can have a universe that is a superposition of many different energy states, but then as decoherence happens, and as the universe evolves, you can sort of sample from fewer and fewer different values of the energy so that the average energy for your branch of the wave function changes over time. So that's an interesting feature of quantum mechanics. Now, it's explicable and perfectly sensible within many worlds. It also happens within the Copenhagen interpretation, but it makes much less sense, like many other things in the Copenhagen interpretation. Okay. Now, what does that have to say about the overall energy conservation? Well, when you do this branching, you are literally taking a pre-existing single branch and decomposing it into other branches that are shorter, right? Their amplitudes are smaller. What matters is that, number one, the total energy of all the branches is 100% super duper conserved. All conserved quantities are 100% conserved in all the different branches, and in the sum of all the branches all at once. That's just perfectly crystal clear. But what's interesting and sort of understated when you discuss quantum mechanics is from inside any one branch, you don't see the other branches, and you don't know that the amplitude of your own branch has shrunk. You don't know that you are now part of a world described by a smaller vector, right, that has absolutely zero effect on your life. So therefore, you have to distinguish between the overall amount of stuff, energy or charge or whatever, in the wave function of the universe versus the amount that you seem to witness in your branch. So what happens is your contribution to the overall energy of the universe gets less and less as time goes on, but you don't notice because you're stuck within one branch, and to you, the energy is approximately conserved. And the same thing works with charge or anything like that. For the question about information traveling faster than light, I'm not exactly sure what you're aiming at. I suspect that you're imagining putting the other world at some distance that light would have to travel, but different branches of the wave function are not at any distance from each other. There's no space in between them, so there's no need for information to travel faster than the speed of light. You might be aiming at something different, but I wasn't quite sure from the question. So Joseph is asking about, can a world simultaneously split from more than one trunk, which is to say, can we start with multiple smaller vectors and sort of add them together? So multiple branches of the wave function combining in some sense. And, I've talked about this before, but the practical answer is no, that never, ever happens. But it's practical in the exact same sense that, entropy on large scales does not spontaneously go down. It's not that the probability is zero. There's a probability that could happen. But the probability is so absurdly, crazily tiny that there's zero chance you need to worry about it, okay? So in the real world, branches increase in number toward the future, not the past. Now, the questions about the double slit and two-state systems versus continuous systems, I'm not sure I know what is going on here. One thing that I did say, maybe this is answering the double slit question, is the branching only happens when you have decoherence. And again, this is something that I think is the right way to think about Everett. Not everyone does. You might get different answers from different people. The answer is to not listen to anybody but me when it comes to the many worlds interpretation of quantum mechanics. In my way of thinking about it, worlds is the word that we apply to branches of the wave function that are entangled with different states of the environment, not just different little vectors we add together. We only count it as worlds when those little vectors represent different states of the environment. So if you have a single spin, then a superposition of spin up and spin down, that's not two worlds, right? It couldn't be, because there's another basis for the vector space in which it's only one direction in which it's spinning. So the question, how many directions is the superposition involving, is not even well defined, right? Likewise, for the double slit experiment, the electron going through those two slits, it is not decohered. If it were, you would not see an interference pattern on the other side. Then you would have measured effectively where the electron is. So they're not in two different branches. They're in the same branch of the wave function, the two different parts of the electron that go through the two different slits. Okay, and finally, Jeff's question is one I understand the least, so I'm not going to do a very good job here. Maybe you're asking, why is the wave function expressed as a superposition of positions rather than momenta or something like that? And that is entirely a question of convenience. I mean, this is why, going back earlier to the Mad Dog Everettianism question, this is why I don't want to privilege things like position or momentum, because there's multiple ways of expressing the wave function, and you're allowed to use whatever way you want. You need to ask yourself what is most useful, what is most appropriate for the circumstances that you're looking at. But then you say it seems equally plausible that the detector would measure 4 points or a single point or a circle shape or something like that. And now I'm not quite sure where you're going. This is, there's just a physics question. You shoot an electron at a target. Oh, maybe this is what you mean. Okay, so let me read this question again, because you say the double slit experiment, but maybe that's why I was getting confused. You can make an electron gun, right? You can take a gizmo that makes electrons and shoots them at a screen. Indeed, you have TV sets just like that. So the question might be, when an electron hits a screen, why does it make a dot rather than some more complicated pattern? And that has nothing to do with the double slit experiment. The double slit experiment is an example of that, but is usually used to illustrate other points. So if the question is, why does the electron make a dot? The answer is because physics is local. Because the way that the electron interacts with the screen is local in space. So in other words, and that feeds into what you mean by decoherence. Remember, I just said that decoherence has this property that it makes branches of the wave function where systems are coherent in their macroscopic physical configuration. So the electron that's a wave will hit the screen everywhere, but it will interact individually with the different atoms on the screen or molecules or whatever, and they will all either light up or not. But then when they light up, they emit light, and that light is then part of the environment, right? I mean, we can see it and we can interact with it. Other light particles go away. So the wave function branches. And the wave function branches separately into worlds that represent which atom in the screen the electron could have hit, because it becomes decoherent, because they emit light in different directions. So I guess it is a confusing point, because it's a combination of the underlying fundamental laws that say that the electron interacts locally with different atoms that it could hit, and the specific features of decoherence that say that you branch into worlds that are sort of the same in their environment and monitoring the same macroscopic configurations for the stuff in them. I hope that is some help. Okay, Trevor Vilwalk says, after you hearing mention Emerson, Lake and Palmer on a previous episode, I'm curious if you're into any other prog rock or other experimentally inclined music like 20th and 21st century classical music. So part of why I chose this question as one to be answered, I don't have very, very deep answers. So yes, I was, especially like in my college days, very into progressive rock, Emerson, Lake and Palmer, yes, Genesis, Pink Floyd, that kind of thing. But I drifted away a little bit. I still love listening to them, but I don't follow the modern versions of them. And they are related to, like you say, experimentally inclined music, including some classical music. And the reason why I'm answering the question is just to sort of lament that I don't follow music that much anymore. Like I said, when I was in college and grad school, I was really into the progressive rock thing. When I was a young professor in Chicago, Chicago is just a great music town overall. And I, in particular, I was always into jazz also, but I really got to be able to go to see live jazz in Chicago in a way that was just an embarrassment of riches. There was so much good stuff going on. Patricia Barber, Von Freeman, Ken Vandermark, people like that. And here in LA, both, I'm older, settled down, married, have cats, but also, the music scene is different here in LA. And, there's lots of strivers trying to become rock stars, but there's not as many people playing every Tuesday night at 11 p.m. In a jazz club with 20 people in the audience, right? That's just not the scene around here, at least. So I don't know of that scene anyway. I'm sure there's wonderful music going on around here in LA, but I'm sort of past that part of my music-loving career. So I've become staid and predictable when it comes to my music. Like many middle-aged people, I like the music that I grew up with, right? And that's terrible, and I feel bad about it, but, so be it. In my spare time to do new and interesting things, I'm trying to learn new parts of science and philosophy and things like that. I hate to say it. That makes me sound very boring, but obviously I do things purely for fun also. Like that's why you've been subjected to podcasts about basketball and poker and things like that. But I'm not following the music scene as much as I should. Sorry about that. Eamon McGee says, if the universe was in a more dense state in its early stages, would time have passed differently for atoms, quarks, neutrons in the early universe than the present day universe? No. The short answer is no. Again, it depends on what you mean. What do you mean if time had passed differently? Time always moves at 1 second per second. Go back to the AMA last month, and I give a little pep talk about this in the beginning. It's just confusing and wrong for people to talk about time traveling at different rates. What you are allowed to talk about is the elapsed time being different for two different trajectories in space-time that both begin at the same point and end at the same point, okay? So if you somehow, I don't know how you could do this, but if you could take a little clock and attach it to an atom in the early universe, the atom would see the clock moving completely normally, no matter what the two of them were doing together. If you did that to two little atoms and they went on different paths and came back, then they might read slightly different times. But that's nothing special about the early universe. That's just because atoms are moving near the speed of light. Atoms are more generally particles, right? The rule of thumb is when the temperature of the universe is larger than the mass of the particle in natural units, then particles are probably moving near the speed of light. That's kind of what it means, right? To have a temperature above the mass of a particle means that the energy is the average energy per particle is greater than the particle's mass. So most of its energy is coming from kinetic energy, coming from motion. And that means it's moving near the speed of light. To get more kinetic energy than rest energy, you need to be moving close to the speed of light. So anyway, yeah, like if you think about individual particles moving near the speed of light, they will experience different amounts of time. But maybe you mean you could take the collection of all the particles, right? That's a plasma or a gas or whatever, depending on exactly what epoch you're thinking of. And there is a rest frame for the plasma, which is different than the rest frame of any of the individual particles. Just like the atoms in the air you're breathing, they have individual motions, but there's still an average velocity of the air, which hopefully is small in the room where you're breathing it. And so you could say, well, what about that? What about time as measured in that rest frame? And you might ask, so this is why I wasn't sure what you were getting at. You might ask, well, because the universe was so dense, gravity is more important, and therefore is gravity affecting the passage of time in the early universe, right? So again, the answer is no. It's really not affecting it at all. So, and again, there's subtleties here. One subtlety is, again, even if there were a gravitational field, like even if you're near a black hole, that's when there's a strong gravitational field, okay? And that's where there is a strong time dilation effect. But the way to think about that effect is not time's moving faster or slower. It's how do you compare the elapsed time if you go near the black hole to what you would have or what your friend experiences when they're staying far away. And it's much like the twin paradox. If you go near a black hole, hang out there for a while, and come back, you will have experienced less time than the people who just stayed behind. So you might think that since the early universe is very, very dense and gravity is strong, it is kind of like that. But it's not. Why? Because everyone in the early universe is experiencing the same gravitational field. There's no analog of your friend far away. The early universe is uniform, right? The early universe is a plasma which is the same density everywhere. This is one of the features of cosmology that makes it very doable, is that the universe is more or less homogeneous and isotropic and was even more homogeneous at early times. So, and that's not just a technicality. Literally, all of the clocks that were in the rest frame of the plasma of the early universe ticked at 1 second per second. And when we say, the era 1 second after the Big Bang, that's what we mean. We mean time as measured by clocks that are in the rest frame of the plasma of the early universe. So that really is 1 second after the Big Bang. There's not some other number of seconds that you really should be using. We're telling you the right answer there. Okay, Umberto Nani says, for cosmologists from planets located in the remote future, those who live in galaxies getting away faster than light from all the other galaxies, are they condemned to think their galaxy is all of the universe? Or is there something being printed in the fabric of space or in the last scattering surface that can tell them how to know more? Well, there is sort of what happens is a good question. Our universe is expanding and also accelerating. So let's imagine that the acceleration continues forever. That's the easiest thing to imagine. The most probable thing is true. It might not be true, but let's imagine that's what's true, okay? So galaxies that we see today, if you did the dumbest thing, if you forgot that there's relativity and you just said, well, the universe is expanding and the galaxies are moving away from us. And so at any one moment in time, there is a distance to the galaxy and there's a sort of rate at which the universe is expanding. So I can figure out an apparent velocity and it will eventually become greater than the speed of light. All that is true. But what is really relevant is the galaxy is emitting light toward us, right? And the light is becoming more and more redshifted. So just like something falling into a black hole, the light from that thing becomes more and more redshifted, and there is a moment that is the last moment in the history of that object that we outside observers will ever see. The same thing is true for galaxies that are being accelerated away from us cosmologically. They will get redder and redder, and we will get less and less information from them. And there is a point in their evolution locally, from their point of view, that we will never see because the light just never gets to us. So, but it's more than that, because not only do the individual photons we see from those galaxies become red, we see fewer and fewer photons, right? If you're emitting a certain number of photons per second in your rest frame, there's more and more time in between those photons from our rest frame. So not only do the galaxies get redder and redder, they get dimmer and dimmer, and there is less and less information to be received from them. The same thing is true for the cosmic microwave background. It continues to be redshifted. Right now, the typical wavelength is, millimeters or centimeters for CMB radiation. It's going to grow longer and longer. Eventually, it will be miles or kilometers or parsecs or megaparsecs or billions of light years if you wait long enough. So if you really do wait long enough, all the other stuff in the universe will fade away and it'll become invisible. And will those people be able to guess or hypothesize that they came from a bright, shiny universe like we live in today? I don't know. I do think that there's a point in principle where it becomes very, very, very hard to do. But again, I'm not very good at predicting future technology, so I'll be silent about that. David DeCloet says, do we only need many worlds because our consciousness doesn't observe superposition, or are there other reasons unrelated to consciousness why we can't just assume there is a single world which is forever in superposition and just more and more entangled? So I think that you make a slight hypothesis contrary to fact there, where you say we can't just assume there is a single world forever in superposition. That is exactly what Everett says. There is a single wave function of the universe, which is forever in superposition and is more and more entangled. But within that wave function, we are allowed to describe it as multiple non-interacting worlds. That has nothing to do with consciousness. Nothing, nothing in quantum mechanics has anything to do with consciousness. The only time that words like consciousness or awareness or agency should come into discussions of quantum mechanics is when you are specifically trying to describe what conscious agents see. If you don't want to, then you don't ever need to use those words, okay? But you still would have branching of the wave function to the extent that it would be possible and helpful to break up the wave function of the universe into individual branches that evolve independently. That's something you're allowed to do. It is precisely the same as saying that if you were Laplace's demon, you could discuss all of the molecules in a box of gas individually. You know their positions and momenta. Therefore, you don't need to use words like temperature or entropy. That doesn't mean you're not allowed to use words like temperature and entropy. You can calculate them. And likewise, if there were no conscious creatures in the universe, you could still figure out what the branches are and when they were happening. But you wouldn't need to if you had infinite information. But none of us does. That's the way the dynamic goes. Gordon Bamber says, if gravity were a repulsive force instead of attractive, how would this affect the arrow of time? So the zeroth order answer here is not at all. There's no direct connection there. The reason why I bring it up is just to mention an interesting paper that I don't think is right. I don't agree with it, but I could be wrong, and it's an interesting paper. It was by Brian Greene, previous Mindscape guest, and Kurt Hinterbichler and some other people back in the day, a few years ago, where they said, look, what we're trying to explain when it comes to the arrow of time, what we need to explain is why the early universe had low entropy. After that, most of it follows, roughly speaking. And if it weren't for gravity, the state of the early universe famously looks like it's high entropy, right? It looks like a thermal gas. It looks like a very hot, dense collection of particles. So there's this song and dance when it comes to gravity and entropy in the early universe where you say, well, the early universe looks high entropy except for gravity, but gravity is there, so it's really low entropy, etc. So what Brian and Kurt and friends said was, what if you turned off gravity in the early universe? What if, for some reason, gravity were zero at early times, and then everything would equilibrate, right? You would naturally, in a box of gas, you would go to a high entropy configuration, but then somehow gravity turns on, okay? And then the universe starts expanding and becoming crumpled, et cetera, et cetera. So in other words, maybe the early universe was high entropy given its conditions at the time. So for reasons I'm not going to go into now, I don't think that quite works as a cosmological scenario, but I do think there's a relationship between gravity and the arrow of time, very broadly speaking. It's not that it's repulsive versus attractive and that would change things in any obvious way, but they are potentially related somehow. Okay, Gregory Mendel, I presume you're not the guy with the pea pods who discovered heredity, but Gregory says, what if, in the Schrodinger's cat scenario, we replace nuclear decay with measuring the spin flip in nuclear magnetic resonance? So the probability of triggering the position oscillates between 0 and 1. If we let a cycle go by, so there was a time when it is 100% likely the poison was triggered, but wait until the next 0% probability to open the box, what do we observe? And I've edited it out a little bit, but I think, Gregory, you figured out your own question here because, of course, the point is you can have a quantum system that evolves slowly, smoothly, from one state to another. That's fine, and that's perfectly reversible. But what the whole point of the Schrodinger's cat scenario is to let that quantum system interact with a big, messy, macroscopic world. And once that happens, your dynamics is irreversible. So even if it's in nuclear decay, a nuclear magnetic resonance or something like that, if you're observing the phase of the nucleus, okay, then what that means is you are coupling the phase of the nucleus to something big and macroscopic, like a detector. And the detector, once it clicks or doesn't click, that makes a macroscopic alteration of the environment, and that is not going to be undone by waiting around longer. So the question is not what is the dynamics of the system you're observing. The question is, does that system become entangled with the wider world? And once it does, it's done. No going back. Once that decoherence happens, it's irreversible. An anonymous questioner says, would early universe physicists have had trouble guessing any part of the standard model? For example, would they have would it have been obvious that one day fermions would gain mass if the lab couldn't produce temperatures cool enough to break electroweak gauge symmetry. So the point here is the background is we have the Higgs boson. The Higgs boson at early times had a zero expectation value in the universe. That is to say, the average value of the Higgs field at any one point in space was zero. It could fluctuate a little bit around that, but basically it was zero. And then eventually the universe cooled down to a point where we underwent what is called the electroweak phase transition. And now the Higgs flops down from zero to some non-zero value. And it's that non-zero value of the Higgs field in empty space that gives mass to elementary particles, to fermions and W bosons and things like that. So if you were a physicist, if you somehow a very heat-resistant physicist in the very early universe, could you have known that was going to happen? In principle, yes, you could have known that was going to happen. So what you would have to do, in fact, we kind of do something like this. So what you would have to do is measure all the parameters in your theory and then trust your theory, right? So the parameters in your theory include all the different couplings of the Higgs boson to itself as well as to other particles. And then you can ask yourself, what are the dynamics of the field in very different circumstances? Like you have the equations, just a matter of your ability to solve them. And we do that now. We ask whether or not there are other values the Higgs boson could have that under different circumstances, maybe even in the future, right? Maybe our Higgs boson value could spontaneously tunnel to a different value. We don't know. So yes, I think there's a lot of thought experimenting going into imagining these early universe physicists, but in principle, they could figure it out. Now, your question technically was, would they have had trouble guessing it? Maybe, yes. It's very possible they would have had trouble guessing that. The electroweak phase transition is earlier. It's at higher temperature than the QCD phase transition. So back then, before you had the Higgs boson with its expectation value, you didn't have protons and neutrons either. You just had free quarks and gluons. It would have been a very, very different universe in very various ways. I would ask, could they have figured out that quarks would eventually become confined? That's a good question. Again, in principle, they could have, but it might have been hard. Andrew Vernon Smith says, in an interview you had with Kip Thorne, Kip referred to certain parts of the movie Interstellar as crossing the line into impossible science fiction. Could you elaborate on what the evidence that Kip was relying on that proves or tends to prove the impossibility of those parts of the movie? I'm pretty sure he was just referring to the end of the movie. I only vaguely remember it now, but there's that thing where he goes in the library and he's like poking and sending signals and there's time travel and things like that. And all of these were inspired by ideas from modern physics, but none of that library stuff actually could be happening in known laws of physics. None of the interactions, the poking of books and things like that, that's not physics, okay? That's just imagination. That's just fantasy. So I think both Kip and, for that matter, Jonah Nolan, who is technically the screenwriter on the movie, brother of Christopher Nolan, are like, we don't know what's happening. And that was the mind of Christopher Nolan sort of imagined this scenario, again, inspired by physics, but not actually following it. That's what I think he had in mind. All of the stuff with the black hole and the wormhole and stuff like that, that stuff was pretty scientifically respectable. Scott says, if something like the ADS-CFT correspondence is shown to apply to our universe, would that lead you to believe that all of our math and physics are convenient descriptions that don't necessarily have any fundamental reality? Nope, it would not. So I have, I think you have to be a little bit careful about what it means to have fundamental reality, right? Versus being a convenient description. Convenient descriptions are only convenient if they capture some fundamental reality, right? So I think that tables and chairs are convenient descriptions. They are nowhere to be found in the standard model of particle physics, right? They're higher level emergent phenomena. But at the level of everyday life, they're very, very convenient to describe what the world around us is. Likewise, all of our math and physics clearly captures something real about reality. And that I don't know whether you want to call it fundamental or not, but it's real, okay? It's both a convenient description and real. I don't think that you should distinguish between convenient descriptions and fundamental reality. Now, there are descriptions that are false, right? You could be wrong about something. When someone does a card trick and they're tricking you, when they pull a rabbit out of a hat, they might lead you to believe something that was false. Now, that's not reality, okay? So it's not like everything you see is obviously truly reality, but the physics descriptions that really do capture some element of what is happening around us, even if they capture it in an indirect way, are things that I would still count as part of fundamental reality. I'm going to group two equations, two questions together here. Nate says, in many worlds, we assume that the world we interact with is a branch of some universal wave function. Do you know of any ways to describe what we think of as causality or locality within the context of our branch on the scale of this universal wave function? And if so, what are they? And then Keith says, in the semi-classical gravity of Hawking radiation, what is the classical part? So I'm grouping these together because they both get at a slightly thorny, but not completely incomprehensible issue, which is how the classical limit arises in quantum mechanics. So Keith says, what is the classical part when we say semi-classical gravity? That's the easy one. Semi-classical gravity is just classical gravity, classical general relativity, right? Classical space-time, but quantum fields on top of that classical space-time. So the quantum fields on top of the classical space-time can even include quantized fluctuations in the gravitational field, so gravitons and things like that. That's why it's semi-classical gravity. Quantum mechanics on top of a classical space-time. And to go back to Nate's question, we have the story that we tell in many worlds about branching, decoherence, all that stuff, right? And what I said earlier was that these branches have the feature that they sort of pick out special pointer states which are coherently arranged in physical space. They have macroscopic shapes and sizes and locations, okay? Whereas if you have a superposition of two things with different locations or shapes or whatever, they would decohere right away. The things that persist as long-lived, robust states are those that sort of look classical, right? Now, that is a very... when you say that out loud, you probably say, oh, okay, that kind of makes sense, right? But it actually requires a lot of work and thought to show that that is what is going on. I mean, this paper I recently wrote with Ashmeet Singh, recently might be like last year. Yeah, last year. So it's still pretty recent. It's got published recently. Called Quantum Mereology. So we ask the question, given this big Hilbert space, how do you divide it up into subspaces, like an environment and a system, for example? And what we suggested was that what we're doing is looking for classical behavior. Why are we looking for classical behavior? Well, maybe anthropic reasons, or maybe sort of non-anthropic reasons that have to do with algorithmic compressibility or simplicity or robustness. I don't know exactly, but who cares? What we said was, let's look for classical behavior. Let's ask how we divide up Hilbert space into subsystems so as to get classical behavior. And what we found is there's actually two aspects to classical behavior. One is the thing that you're looking at, the baseball or whatever, it follows a classical trajectory and it doesn't spread out all over the place, right? If you launch a rocket toward the moon, you don't need quantum mechanics to get it there. It will more or less move on its classical Newtonian trajectory. And the other one is that you're in a pointer state. In other words, the state that is described by the branch that you're on is one that doesn't keep getting entangled. This entanglement remains almost constant. And these two different criteria of remaining localized along a classical trajectory and remaining unentangled with the environment, they're different sounding, but they play together. There's some relationship between them, and it's subtle, and we're still thinking about it. So we think that this underlies why there is a difference in the observed world between positions and momenta, for example. But I think this is part of a story that we don't actually have completely explicated yet. But the short answer to your actual question is the way that the universe branches in many worlds is onto branches that individually act as classical as they can. Sometimes they're not going to act classical. There's a Geiger counter, right? We measure a spin or whatever, but that's an incredibly tiny amount of quantum behavior compared to what we do in our everyday lives. And so that feature is not just an accident. That's kind of what defines the branches that we're on, this emergent classicality. And once you get that, you get causality and locality and all that stuff coming just as much along for the ride as it would in ordinary classical mechanics. Robin Quinnell says, is there any physics evidence that we are in a simulation? Nope, there is not. In fact, I would argue that there's evidence that we're not in a simulation. So what do you mean by evidence in this case? You got to be a good Bayesian. You have to ask yourself, what would we expect the universe to look like were we in a simulation versus what would we expect to look like if we were not in a simulation? Now, that's a really hard question to answer. It's very analogous to asking the analogous question about God, right? What would you expect the universe to look like if God existed versus purely naturalism? Well, it depends on your idea about God. It depends on your idea about the simulators and what they're trying to do with the simulation. But what we can tell about our universe is, number one, that it's super wasteful of resources, right? Like if what they care about is us, like if you thought that the simulators care about human beings in any way, then they've made an awfully big universe, most of which we can never get to, and most of which has no effect on us. So you would think, again, it's not a necessary consequence, but if you were to guess, let's put it this way. If you did notice, yeah, this is a good way to put it, right? Okay, so you have two scenarios on the table. One is just reality, naturalism, there's the universe, it obeys laws of physics. The other is we live in a simulation, okay? And there's two options. One, and there's sort of two pictures of the universe, which we can on broad principles distinguish. A big universe where there's us, but then we're very, very tiny compared to the bigger picture, and there's lots of galaxies and so forth that seems very wasteful and resource intensive that we have nothing to do with. Or there's a small universe, right? Like that the universe as a whole is more or less human scaled. Maybe it's, 1 million times the size of a human being rather than billions and billions of times the size of a human being. What would you expect under these two scenarios of naturalism versus simulation? Well, here's what I would say. If we did live in the tiny universe, then you might say, aha, that makes perfect sense to me because we probably live in a simulation, right? That makes more sense to me if we live in a simulation that the universe is human size, that the universe is sort of adapted to our existence here. And if you're going to say that, if you would believe that, if you think that counterfactually, were the universe tiny, we would take that as evidence for a simulation, then it follows logically, and you cannot wriggle out of it, that if the universe is large, you must take that as evidence against the idea that we live in a simulation. Of course, you can wriggle out of it. You can say, well, they're very, technologically advanced. They don't care about resources. They're using very clever optimization algorithms, whatever. But if you think that we would take it as evidence for simulation, were the universe to be small, then we should take it as evidence against simulation that the universe is large. Okay, Maya Apple says, would it be possible to be fully certain in the finality of a theory of everything? Isn't it always possible for there to be a different underlying explanatory system? Sure. Yeah, I don't think that certainty is ever your goal in science at all. Because even if you had a theory of everything that fit all of the data perfectly, you could always do an experiment tomorrow that didn't fit the data, and you would have to change it, right? So this is part of being a scientist. We don't aim towards certainty. We aim towards higher and higher credences. But it's always a mistake to think that, we're getting to 100% belief in our theories, because that would be bad. That would mean we could never change our minds in the future. That's not how scientists should work. Okay, the final question is Jim Murphy says, the universe is really big. To me, this is distressing. I don't know if this relates to the simulation argument whatsoever. But he says, to me, this is distressing not because I'm afraid of how small we are, but because of a kind of cosmic FOMO. For those of us who are too old, FOMO is the kids' way of saying fear of missing out, FOMO. The disappointment of knowing that there is so much out there that we will never discover is sometimes too much to handle. Do you ever get these feelings, and how do you remind yourself that there is plenty to explore here on Earth? So this is the final question, so we can be a little bit relaxed about it. I don't get those feelings. Those are not the feelings I get. In fact, the opposite. Like, what if we were almost done? What if we'd almost discovered, or had discovered everything interesting to be discovered about physics, politics, economics, whatever, chemistry, biology? What if we basically knew everything? That would be terrible. Like, that would be, I'm sure that we would think of ways to keep ourselves interested and amused, etc. But the fact that we live in a universe where there are so many things yet to be discovered makes me happy. Well, especially because we have discovered a bunch of things, right? Like, my perspective is obviously highly parochial and limited because I don't know what things are going to be like 1,000 or 1,000,000 years from now. But in some way of thinking, we live in a pretty good part of intellectual history where we've learned a lot enough that there's not a lot of child mortality, etc. We can go much farther, getting rid of poverty and disease and curing aging and things like that. So I think that probably, unless we do something dumb, 100 or 200 or 1,000 years from now will be better than now. But over historical timescales, comparing us now to 100,000 years ago, we're doing a lot better now. But there's still a lot to be discovered, right? Right here on Earth. And so I do not have any of this fear of missing out. Like I don't even in much more down to earth circumstances, fear of missing out is not something I have. It's not even something that makes sense to me because the question is not what are you missing? The question is what are you experiencing, right? As long as you are experiencing all sorts of good stuff, the fact that there's other good stuff that you're not experiencing is just something I couldn't even imagine caring too much about, right? If it's literally something that I could go and experience and it would be even better, then fine. But then I'll be missing out on the other thing that I'm getting now. So sure, you should work to sort of have an interesting portfolio of experiences. That sounds like a very reasonable, attainable goal. But to experience everything, to learn everything, to do everything, like, no, and I have no interest in even trying to do that. It's about the journey, right? We are these little tiny bits of self-organization that feed off of the free energy around us for a finite period of time in a very finite world of experience. But that world of experience is still way larger than we have the ability to experience. So I'm not worried about all the experiences I can't have. I got enough to worry about with the experiences I do have. All right. Thanks for sticking with me. I can feel the voice beginning to go. Thanks for supporting Mindscape, as always. It's been tough times. I'm getting vaccinated. Tomorrow, I get my second shot as I'm recording this, so I'm very happy about that. Hope everyone out there is getting vaccinated. If not already, then very soon. Again, I hope that the podcast has been a little bit useful to folks in these weird times of ours. And it's certainly been extremely wonderful for me to have so much support from you out there for Mindscape. And I look forward to what it has coming up in the future. All right, take care. Bye-bye.